Instrumentation, NT-AAI, we would like to take a moment to welcome our distinguished guest and invite them to the dais to honor us with their presence.
It is my great honor to invite Dr. R. Krishnan, Director of the Indian Institute of Tropical Meteorology, Pune. Now, it is my great honor to invite Dr. D.K. Aswal, Director of Health and Safety Group, DARC, Mumbai. Namaste.
Now I welcome Professor S.N. Tripathi, Dean, Kotak School of Sustainability, IIT Kanpur, and President of IASTA. Welcome, sir. I welcome Dr. G. Panditore, Project Director of Atmospheric Research Testbeds, IITM. I welcome Dr. Vinu K. Valsala, Project Director of Development of Skilled Manpower, DEST, IITM, and Coordinator of the NT-AAI workshop.
Thank you all for joining us on this special event. We look forward to a wonderful event ahead, enriched by your presence and wisdom. Welcome.
At this time, I would like to invite our esteemed director to come forward and present a bouquet to our distinguished guest, Dr. D.K. Aswal. Now I request our director to present a bouquet to Professor S.N. Tripathi. Now I would like to request Dr. Panditore to present a bouquet to our director.
Thank you.
I request Dr. Leena to present a bouquet to Dr. Panditore. I request Dr. Leena. I request Dr. Leena to present a bouquet to Dr. Vinu Valsala.
Yes. To formally commence today's event, it is my great honor to invite the person whose vision and leadership has guided this initiative. Please join me in welcoming our respected director, Dr. R. Krishnan, to the stage to deliver the welcome address.
Dear esteemed delegates on the dais, our chief guest, Dr. Aswal from BARC, Professor Sachidanand Tripathi from IIT Kanpur, my colleague Dr. Panditore, Project Director, Atmospheric Research Testbed, Dr. Vinu Valsala, Project Director of DESK, and all the participants of this meeting. First of all, namaskar and welcome you all to IITM for this important workshop on national training on atmospheric aerosol instrumentation. And I'm very happy that the participation is very good. A large number of people have come, and also very nice to see Sachida, my good old friend, who's today's chief guest, and also Professor Aswal, whom I'm meeting for the first time. And I'm very glad that Dr. Pandya has organized this workshop, training workshop on instrumentation, on aerosol instrumentation. And as you all know that the climate change is already happening, greenhouse gases are contributing to the warming, but also regionally, aerosols are also affecting the climate by cutting down the solar radiation and so on. And we have seen that it has impacts on the water cycle. Only thing is the spatial variability of aerosol, spatial and temporal variability is very large. And the species, the large species in the atmospheric, different number of species, and their optical properties are very different. It makes it difficult. And more importantly, they are also having profound impacts on health. Now, once the winter season starts coming, as we are heading towards it, we are going to see that lot of pollution issues, air pollution issues in North India, in Delhi. So it has both in terms of climate as well as health. Atmospheric aerosols are becoming more and more important. And we understand very little of that. A lot of progress has been made over the years. And even this kind of variability, large spatial and temporal variability, observing them is very important. And already there are a good number of observational studies, also modeling studies. We have observations from the satellite. But I think augmenting it and coming out with periodic assessment, because the concentrations are changing continuously. And some places they have cut down the aerosol emissions due to the regulation norms, and some places it is increasing. So it's a very complex system. So continuous monitoring, both the ground-based as well as space-based observations are going to become very, very important in the coming years. And also atmospheric chemistry is becoming more and more important as we see. So the key for this is instrumentation, of course. So I'm very glad that Dr. Pandithurai has taken up this initiative, having a training program on atmospheric instrumentation, aerosol instrumentation, which is very timely. And so I really welcome this initiative, and I'm very happy to see a large participation of participants from different parts of the country, and maybe outside India as well. With this opening remarks, I welcome you all and thank you very much, Professor Sachida and Satyanan Tripathi and Dr. Aswal for joining this meeting, and all of you. Thank you all.
Thank you very much, sir, for your inspiring words and for officially setting the tone for today's event.
As we continue, it is now time to introduce an important organization that is playing a pivotal role in the atmospheric science community, Indian Aerosol Science and Technology Association, ISTA. It is my distinct honor to introduce Professor S.N. Tripathi, Dean of the Kotak School of Sustainability, IIT Kanpur, and President of ISTA, a distinguished laureate of the Shanti Swarup Bhatnagar Prize, J.C. Bose National Fellowship, and the Infosys Prize. Professor Tripathi has made significant contributions to climate change, air quality, and nuclear safety. His pioneering research includes evidence of the aerosol-induced cloud invigoration effect during the Indian summer monsoon and the establishment of National Aerosol Facility for enhancing academia's role in nuclear safety studies. Professor Tripathi's innovative sensor-based urban air quality monitoring network has revolutionized real-time source apportionment across India. As an experts training committee member, he has formed an alliance of technical institutes to support the National Clean Air Program, building capacity in air quality management nationwide. Professor Tripathi is a leading figure in his field. To give us an overview of ISTA, I would like to invite Professor S.N. Tripathi, President of ISTA, to the dais. Please.
Good morning, everyone. Professor Dr. Krishnan, Director IITM Pune, Dr. Aswal, Group Director, RPAD, VRC, my good friend Dr. Pandithurai, Dr. Vesala, and all my dear participants who have come across the country to attend this timely workshop, as Dr. Krishnan pointed out. And I thank the previous person who introduced me. I think it was not the occasion to read out my bio, but nevertheless, I thank her for her kind words. So, as you know, that ISTA has been in the existence for about something like 3.5 decades. And we know that aerosol community has grown from probably few scientists in the country. Maybe Dr. Krishnan is an old hat here, older than me, certainly. that he would recall that probably in early 90s and late 80s, there would be few people who would be doing aerosol research, probably one or two in BARC, couple of them in ISRO, and couple of them at IITM, correct? And now we know that it has grown probably in few hundreds and maybe close to thousands across the country. So Dr. Krishnan pointed out that atmospheric aerosol understanding of that is definitely a very important issue from the point of view of prediction of climate change. Because aerosols play a very major role in modulating climate. And we have made some good progress there in last 3 decades because the community grew, our knowledge grew along with. We could establish new networks, observational, and also doing some point measurements. And we have further the atmospheric aerosol science. But I also must point out to you, because many young participants are here and some of them will carry this legacy forward, that this organization, as you see, is Indian Aerosols Science and Technology Association, right? So you have that a mandate for this organization to provide a platform for connecting between aerosol scientists, engineers, and technologists. And as was pointed out, that we have done very well in aerosol science, or we have done reasonably well in the global context. But when it comes to engineering and technology, I think we need to really reflect that whether we have done so well. And it seems that in these two aspects, probably there is need to do a lot more. For example, when it comes to the aerosol engineering, our contribution to the softwares which we use on a day-to-day basis, be it air quality prediction, or where these modules enter into different kind of CFD simulation platform, computational fluid dynamics platforms, I'm not aware of that we have made a lot of progress there. Instrumentation is the theme of this workshop, but most of the instruments which we are gathering here are all possibly imported, maybe with the exception of 1 or 2. So I think there is a greater need today that one, if we want to cut down our over dependence on the imports of these instruments in order to do cutting edge research, and that is where we save the money, certainly. It spurs the innovation in the country, and at the same time, you don't lag behind in doing the cutting edge research. Because when you make your instruments, then you set the agenda for research. Now, if others make the instrument, then they set the agenda and we follow it. So that's, I think, very, very important. And I'm mentioning it as a voice, voice on, or representing the collective voice of IASTA, because we have 2 people who are sitting on the dais, IITM director, who I'm sure speaks to policy makers who decides the policy on climate change related research in the country, and Dr. Aswal, who also sits with the atomic energy leadership, that how collectively we can create some program, some schemes where the new generation can be brought into making of instrumentation. That's very, very important. Now, coming back to IASTA, we have a very energetic and active secretary in Dr. Manish Joshi, who is sitting here. I think you already know through your correspondences in the last few weeks or month pertaining to this workshop. And he and his team has really been driving the IASTA activities in last possibly 1.5 years, and this has been tremendous. He has been able to organize probably 20 plus webinars, which were joined by some of the top people, top aerosol researchers across the world. And he has plans to organize many outreach programs for school kids. You know that our flagship event, the biennial conference, which is attended by all of you and many more, is very well coming by end of this year, sometime in 3rd week of December. I think it has become now an annual event, so you are all very well cordially invited to attend that. Then, as a follow-up to this meeting, what we are having today. I must thank again Dr. Manish Joshi and other BRC colleagues, and in equal proportion, the contribution made by Dr. Pandit Thurai and his team, that this is, of course, very, very delightful to see that we have had 160 plus applications. So I'm sure you must be feeling very proud that you are the 50 odd or 55 odd who are selected for this meeting or this workshop. So you must take fullest advantage of this. You will have this theory sessions or lessons. You must learn whatever is being taught in the class, and then you will have hands-on training in the afternoon every day. And then there are some program that where you will be recognized who will do very well. I think they will get some commendation letter, etc. So you should do very well. We will have a follow-up meeting like this. So you keep your eyes and ears open, as Dr. Manish Joshi tells me, that will focus on modeling, just like we are doing on instrumentation. We'll have a solely modeling focused meeting or workshop very soon. And I hope that we'll have participation in equal measures like we have today. So with that, I again invite you, welcome you on behalf of IASTA, and I thank IITM Director, Dr. Pandit Thurai, and everyone who has made it possible. Thank you so much.
Thank you, Professor Tripathi, for providing us with such an insightful introduction of IASTA.
It is now time for one of the most awaited moments of today's event, the inaugural address. We are honored to have with us a distinguished leader whose presence elevates this occasion. Dr. Dinesh Kumar Aswal, a senior member of the Trombay Council at DARC, holds pivotal roles, including Director of the Health, Safety and Environment Group and National Radiation Emergency Response. He oversees nuclear and radiological safety across the nuclear fuel cycle, ensuring public safety in collaboration with national and international bodies. An acclaimed scientist and science diplomat, Dr. Aswal has authored over 500 publications, edited 12 books, and holds 9 patents. He has led key institutions such as CSIR, NPL, and CERI, and developed critical technologies for India's nuclear program and public safety. His Aswal model of metrology infrastructure fosters synergy among government, academia, and industry, elevating India's measurement standards globally. He established the National Atomic Clock Ensemble for IST synchronization and has driven numerous national programs benefiting sectors like nuclear safety, digital security, and quality control. Dr. Aswal's contributions have earned him prestigious awards and recognition as one of the world's top scientists. It is my privilege to invite Dr. D.K. Aswal to deliver the inaugural address.
A very good morning to all of you. Good morning. As has already been told by Dr. Krishnan and Dr. Tripathi, that aerosols are very important. Important for climate change, understanding. Important for its health hazard. And in general, therefore, aerosols are treated as bad. Do you agree with me? Aerosols are bad? Yes or no? Or aerosols are good as well? What is your opinion? Speak. They are good also, they are bad also. It depends upon the concentration. And aerosols are very, very tiny particles, which are suspended in air. And most of the time, until unless you have got the optical properties affecting, they are invisible. And therefore, there is a balance between the radiation and the aerosols. So what do you feel? Radiations are harmful? Yes or no? All the time? Yes. So therefore, if you talk about the radiation, you talk about the aerosols. Most important part is that general perception is that both are bad. And this misrepresentation that the aerosols and radiations are bad is based on the linear no threshold model. Means anything is harmful. And that is basically because there's a lack of scientific evidences at low doses. So imagine if there is no aerosols on the surface, on the Earth atmosphere, what will happen? Anyone? Loudly. Will there be any rain? Why? Because it acts like a nuclei center for the rain, right? Similarly, if there is no radiation, what will happen? So I don't know whether you are aware or not. While you are sitting over here, do you know how many gamma photons are passing through your body? Roughly 1 lakh gamma photon per second. Whether you want or don't want, they are penetrating through your body and they are roughly 1 lakh per second. What do they do? So the science of that is not known. Similarly, the aerosols, by and large, they were treated as okay, they will begin, but in terms of health. So there have been a large number of aerosols production methods. Instead of injecting your vaccines, people inject through nasal aerosols. So apart from the what Professor Krishnan and Professor Tripathi they mentioned, that we need definitely to understand the aerosols dynamics, their preparation, their mechanism of transportation, the modeling, and most importantly, the equipment, which Dr. Tripathi even highlighted. Most of our equipments are imported, as well as the models. So we have to work upon that. What I'm trying to tell you, the another domain, how does the aerosols and the radiation, they interact with the human body? If somebody has got the lungs infection, all the time they will give aerosol spray because surface to volume ratio is very large, and therefore the efficacy of the medicine is very, very high. Now, aerosol transportation, if you don't understand well, particularly in the case of the nuclear industry, it can lead to a chaos. So one of the fundamental point is that any radiation and aerosols is harmful to the human being. That was one. And the second is that if you don't have the appropriate modeling, where and how these aerosols are going, there is going to be a big problem. And how many of you heard of, raise your hands, have heard of Chernobyl and Fukushima accidents? Nuclear accidents of Fukushima and Chernobyl. You see, in both the cases, in Chernobyl and Fukushima, both the nuclear reactors were blasted. And when the nuclear reactors are blasted, since they are at a very high temperature, so whatever the nuclear materials are there, they form in the form of aerosols and they spread. Now, in both the cases, in Chernobyl and Fukushima, they were spread across the various areas. No, the modeling was not known. They were very weak. People didn't know where those aerosols have gone. You know what step they have taken? So number one, any aerosols and particularly radioactive aerosols is very, very harmful. And number two, they will be spreading across the one. They have evacuated more than 2,500 square kilometers in and around the plant. Now, there were many predictions made. In case of Chernobyl, it was presumed that Chernobyl accident took place in 1986. Now, it was presumed that roughly 60,000 to 90,000 people will die because of cancer. because these radioactive aerosols will go in your body and that will cause you cancer. And after 25 years of ingestion period, people are likely to get the cancer. Now, when there is a nuclear accident, there are two types of aerosols which come out. One is the iodine 131, another is the cerium 137. Of course, little bit of strontium 1. Now, what was happened was that since there was no good prediction, 60,000, 90,000 were assumed, a large number of area was evacuated, and more than 1 lakh pregnant women were asked to go for abortion. Now, when you look back, how correct those prediction went? Do you know how many people died because of the solid cancer? 0. Not a single person has got a leukemia or solid cancer. Only 15 boys or girls, they died because of the thyroid cancer. And how many people they evacuated? 6 lakh people. So out of 6 lakh people, if 15 die, anyway, they will die anyway. So the lack of science studies, namely the effect of aerosols on the human body, and the wrong prediction models, both gave a very negative popularity for nuclear energy. Same thing happened in Fukushima, in Japan. Not a single person died because of radiation or because of the cancer associated with it in long term. But they evacuated large area, several thousand square kilometers. And while evacuating, they not only spent of money equivalent to the $55 billion, but also killed 1,600 people while transporting them. And look at the conditions. When the Fukushima accident took place, there were many hospitals where there were many patients in the ICUs. They were on the oxygen support and this and that. Now, all of a sudden, they say that, no, you have to evacuate it because after 20 years, you may get a cancer. So it is your betterment that we are evacuating you from the hospital. You know what happened? The moment this life support system was removed, they died immediately. So wrong science, wrong policies, without deeper knowledge, can create this kind of casualties. So abortion of so many women in the Europe because of the Chernobyl, because now they are facing the population problem, killing so much of ill people directly during the evacuation, that created a lot of problems. Now, worst part was in Chernobyl, when the accident took place, they evacuated 2,500 square kilometers. But very few knew that the aerosol that was generated has deposited in Sweden and Norway. Because you do not know that depending upon the the wind direction and meteorological condition, where they will deposit. And in Fukushima, same thing happened. They evacuated from a place where there was no radiation, and they evacuated and deposited them in a place where there was more radiation because the plume went in that direction. So therefore, from the point of view of nuclear industry, the understanding of aerosols, their modeling, their deposition, it becomes very, very essential. But more than that, what is required to be understood is that how the aerosols affect on the biological system. Now, there are many studies. For example, if you go to the Japan or you go to the Germany, they have got a centers which inhale the radon. Radon is again a radioactive material. They have got spas, they have got caves. And if you have got a kind of problems, health problems, so people say that a limit quantity of radioactivity is good for the health. And it can cure a large number of diseases. And the scientific explanation for that is, in our biological system, you have got a normal cells, they perform their duties, and you have got immune cells. And immune cells are essentially your army, which fight against the diseases. So it appears that nature has given you this radiation, which I was telling you, 1 lakh photon per second through your body. And the additional, if you take little additional one, that stimulates your immune system. And therefore, any kind of disease that can be taken care of. So there are large number of such radon therapy, or we call that a low dose ionizing radiation therapy systems in Europe and in Japan. But unfortunately, none of them in India, because we strictly followed that any radiation is harmful. We follow that, and therefore we don't have any kind of problem. Similarly, in Brazil, if you have got a problem like arthritis, your knee problem, so they don't take that medicines. They take the radiation therapy using the sand, which has got a very high kind of radioactivity. So what I'm trying to say that it is important to understand the aerosols, their modeling, their propagation, their transportation, their deposition, their instrumentation which are required. And I'm very happy that the ISTA and the IITM, they have taken this initiative where they are going to teach you from the very basics about these aerosol properties, and not only about that, about the equipment and instrumentation. And I was talking to Dr. Manish, he was saying that they are going to open the instrument and show you that how they function. Okay, so they are going to surgery for you for the equipment, so that you understand in detail how these instrument do work. But nevertheless, you should think one step behind that. How does the aerosols help or degrade the biological systems? There are many animal studies. For example, your mice, what they do, they introduce a cancer in it. So there is a tumor. And then they are asked to inhale the radioactive aerosols. And it has been seen, there are large number of studies now, the tumor itself goes away. So you don't have to do that chemotherapy, the radiotherapy, you don't have to do. So limited of radiation dose in the form of the soft aerosols can create a repair mechanism in your body. And that is the futuristic science. Low doses, radioactive material to treat the disease in your body. And therefore, one should know how to create in a very quantity, how to measure the concentration, how much should be given. Because by and large, the human body, they follow the biphasic effect. Biphasic effect means if you take a dose and response. So at low doses, it is good. At high doses, it is bad. How many of you like sweets? Raise your hands. Almost everybody likes it. Now, if I give you 1,000 rasgulla or 100 rasgulla at a time, will you be able to eat? Why? You know that you will become ill. Your stomach will become upset. But if I give you only one, then you will say probably I can take one more, or maybe one more. 3. So there is a threshold value. There is a balance between the good and bad. And the combination of good and bad is true for each and everything. How many of you have taken the corona vaccine? Almost everybody. And what is there in the corona vaccine? The dead virus itself. Now, if you say that we are inserting dead virus in your body, will you accept that? But the moment you say we are giving a corona vaccine, you will accept immediately. But essentially, it is a dead virus because, again, it is a dose response curve. At low doses, it is activating your immune system. So, when it is activating your immune system, it is good for you. So, therefore, the new type of aerosol for the health studies, that should also be looked into that. And aerosols are everywhere. I know one of my colleague, professor in Weizmann Institute of Science in Israel. So one of the biggest problem in automotive industry is that bearing. So you want a very good, smooth movement of the parts. and therefore there are large amount of lubricants used. So what this scientist did there, he published a lot and he is a billionaire now. So in lab, he made the MOS2, molybdenum disaccharide, which is a two-dimensional layer material. He knew how to make a aerosol suspension of that. So he and his two students, they created this one, and now it is used worldwide in everywhere in automotive industry. So you put 2 drops, it goes there, and MOS is very hard. It is a flexible also. So it works like a very good aerosol. So what I'm trying to say that if you understand the physical properties, material properties very nicely, you can become billionaire by working on the aerosols. So aerosols have got large applications. I've highlighted few of them. And I hope not only you will understand them, but try to understand and find out the application of aerosols also. And nowadays, as we say in the government department, don't be a job seeker, become a job provider. And when you want to become a job provider, you have to learn the intricacies of the science and technology, their application, their market value. And once you do that, anybody can take up. And I'm very happy that there are large number of girls who are there in this aerosol conference. And nowadays, girls, they know how to make things. And I'm sure that there will be large number of entrepreneurs which are coming up from this workshop. So with this, I open this workshop and I wish you all the best. Thank you very much.
Thank you very much, sir, for your inspiring and thought-provoking inaugural address. Your words have truly set a powerful tone for this event, and we are deeply honored by your presence and your insights.
Now, to give us a brief introduction and outline the objectives of this workshop, I would like to call upon Dr. G. Panditurai, Project Director of Atmospheric Research Test Beds, IITM, and also Executive Committee member of ISTRA and Scientific Advisor of this event. Please welcome Dr. Panditurai.
Very good morning to all of you. Respected Dr. D.K. Aswal. He gave an excellent inaugural address and set the tone for this training workshop on atmospheric aerosol instrumentation. So he has mainly covered the health effects of aerosols, and also Dr. Krishnan and Dr. Professor Tripathi mentioned about the climate effects of aerosols. So in IITM, we mainly deal with the climate and also health effects. For climate effects, we need to understand the processes which are relevant to aerosol cloud interactions. That is one of the major process, which is aerosol cloud interactions is not very well represented. So on this account, we also have 2 great teams from both BARC and IITM. So the course was structured like this. So we were covering the broad topics such as aerosol sampling by different techniques and measurements and instrumentation, aerosol generators, which are mainly used for from nanoscale to microscale for calibrating the instruments, hygroscopic growth and aerosol cloud interactions, aerosol charge measurements, chemical measurements, and physical characterization such as scattering, absorption, and aerosol radiation interactions, low-cost sensors. Then we are also covering the ice nuclei measurements, which is not very well understood, and bioaerosol characterization. So this workshop is proposed to address both instrumentation and measuring techniques for studying different atmospheric aerosols and characteristics. Along with the basics of aerosols, we will be giving a description and working principle and of different aerosol instruments. And we have afternoon session, as Dr. Aswal mentioned, that you will be able to see how the instruments work and how you could process the data set. So this will provide a unique opportunity to share expertise of seasoned researchers with students and early stage researchers and technocrats. I also want to mention the response to this workshop is overwhelming. So we could shortlist only 60 odd people, considering the logistics such as accommodation, hostel accommodation, etc. Also, we have some professional participants, some early career researchers. We have resource persons from major academic institutions, IITs, IIT Kanpur, IIT Madras, and central universities, and research institutions such as PRL, BRC, IGCAR, and also IITM. At this junction, I want to introduce our ISTA Secretary, Dr. Manish Joshi. So can you please, so he has taken excellent initiatives to merge both IITM and BRC to take up this task. So IITM has been closely working with the BRC because from the beginning, the ISTA is originated from BRC and they continue to interact with IITM. And so we are nearby, both Pune and Mumbai, so we were able to host this. And we also have a unique high altitude cloud physics laboratory. As we mentioned that without aerosols, we can't have a clouds and precipitation. So we'll be able to visit that observatory in Mahabaleshwar on Wednesday, being a closed holiday. We will have an excursion to our laboratory and see all the instruments working and how we how we try to understand the aerosol cloud interactions, which is one of the major uncertainty in climate system. So with this, I will again welcome you all and thank all the dignitaries, especially Dr. Aswal and Professor Tripathi, to grace this occasion, and I thank Director for gracing this and giving full support to organizing this workshop. Thank you very much.
Thank you, Dr. Panditare, for that excellent introduction to the workshop.
As we continue our program, it is my pleasure to introduce a key figure who has been instrumental in the development of training initiative at our institution. Please join me in welcoming Dr. Binu Balsala to the stage to provide us with an overview of the IITM Training Center test and its significant contributions to our field. Welcome.
Thank you, Abhishek. Very good morning to all of you. Professor Tripathi, Dean, Kotak School of Sustainability and President IASTA. Professor Aswal, Director, Health, Safety and Environment, BARC. Director Sir, Pandit Saab, and Dr. Manish, Member, Convener, IASTA, and dignitaries of the dais and the participants for these workshops, and my friends and colleagues. So it is our great pleasure to welcome, first of all the participants come from all the way from various parts of India to be part of this workshop. So my task is to introduce our program. So what is that's a development of skilled manpower. It is a dedicated program by the Ministry of Earth Science and operating at IITM. So what this program do, it identify the gap areas where the students and the upcoming young researchers and scientists require training, particularly so that they will develop their skill in a particular aspect. So under this, we have various initiatives, and one of them is to conduct training workshops of a duration of a week or up to 10 days. So probably many of you participants might have heard of our earlier activities, and we conduct these activities regularly, several activities in a year. So this activity is one of them, initiated by Dr. Panditare and Dr. Patnakumari, because he's here, and with IASTA members. They had this idea, why don't we conduct a training workshop jointly on this aerosol topic, and especially focusing on science and instrumentation of aerosol. So why this training needs to be taken up? Because as you know, the conventional educational system in universities has very little facilities to expose the students to this instrumentation and cutting edge research in a particular topics going on in the world. So this program is dedicated to give an opportunity for young people to come meet scientists who are working on the frontier areas of the subjects get to know about the instruments, technology, methodology, modeling, and all aspects of theoretical sciences, and get an idea and hands-on training on those. For example, these instruments are very quite expensive instruments, and not every research labs in India may not be able to afford it. So we have a government has funded research programs, so these instruments can be established. One such facility is a high altitude cloud physics laboratory, where dedicated instruments are kept in focus to address specific scientific problems on cloud, aerosol, and interactions. We will be visiting that facility, and it will be a unique opportunity for many of you to see how this instrument in operation, probably have a chance to put your hand on it and then make some measurements, dummy measurements, and analyze some of the data coming out through that. And so several exciting talks are arranged by key dignitaries in this area. So I hope you all will make use of this. And the success to the participation is that your complete involvement in the workshop. So we request all of you to be present on time every day and keep the schedule, report on venue when we ask to report. And if you have any other help regarding during your stay, our teams are there to help you with. Our training unit coordinators are in the registration. They will help you. And IITM is a very good campus. First of all, another thing that so many students and young researchers are here, participants, and probably this is a chance you can network. You can meet each other and share your ideas. Take it an open discussion. Okay, all ideas are welcome. Sometimes innovative discussions spark through this kind of meetings. Okay, so you are very young. That doesn't mean that you are not able to create innovative. You are already in a right platform to create innovative ideas. So keep discussing and share your information, connect, make a network. So those are the things that you should do in such training workshops. So with this very short introduction, so we welcome all the participants again to this workshop. Make use of this very good opportunity, and thank you.
Thank you, Vinu sir, for the insightful introduction to the IITM Training Center.
We come to the conclusion of today's inaugural event. It is now time to express a gratitude to everyone who has contributed to making this workshop a success. I would like to invite Dr. Padma Kumari, Project Director of LAURES IITM and also Executive Committee Member of IASTA, to the stage to deliver the vote of thanks. Please welcome Dr. Padma Kumari.
Thank you, Sonal. So, good morning to all. So, on behalf of the organizing committee, first and foremost, I'd like to express my heartfelt gratitude to our director, Dr. Krishnan, for his unwavering support in making this event possible. His encouragement has been instrumental in ensuring the success of this workshop, and we are truly grateful for this opportunity to host this workshop here at IIT. So our deep thanks to Dr. D.K. Aswal, Director, Health, Safety and Environment Group at BRC. So we are honored by your presence, and your words have added great value to this workshop. We extend our sincere thanks to Professor S.N. Tripathi, Dean of Kotak School of Sustainability at IIT Kanpur, for his insightful introduction to IASTA and for being here with us to support this workshop. His leadership continues to inspire and strengthen the scientific community. A special thanks goes to Dr. Pandithurai, Project Director at IITM, for his insightful introduction to the workshop and also for his crucial role in organizing this workshop. His guidance and leadership has been vital in shaping this program. So we would like to thank Dr. Vinu Vansala, Project Director, Desk at IITM, and his team for their excellent support for all the arrangements for this event. And we deeply appreciate him and his team's contribution to the smooth execution of this event. So we thank Dr. Manish, scientist at BRC and member convener of IASTA, and also all his colleagues from BRC for continuous discussions, support, and coordination in execution of this event. Now, I sincerely thank the local organizing committee members for their tireless efforts in making logistics, participants, and all the arrangements along with the desk team. And we also thank our computer division General Administration section, Guest House Management at Prithvi, Canteen Management, LIP, and Security for their support and coordination. Finally, I would like to thank each and every one of you who have come from different parts of the country for attending this training workshop. We hope this workshop provides valuable insights and fosters fruitful discussions. Thank you all, and we look forward to a productive and engaging workshop ahead. And I also encourage all of you to visit our high altitude cloud physics laboratory at Mahabaleshwar, which is scheduled on 2nd October, Wednesday. Thank you.
Thank you, ma'am. As we draw our event to a close, we would like to invite all participants to join us for a group photo in front of the Meghdut Hall, followed by high tea. High tea is arranged at the Meghdut Auditorium basement. I would like to request everyone to please gather back in the hall for the upcoming lecture by 11 a.m. Thank you all.
Come forward so that you will be visible.
Please come forward. Please take in the first video. Straight started without any introduction.
Yeah. Welcome back, everyone. Now we will proceed for the lectures. The first lecture is by Professor S.N. Tripathi, Dean, Kotak School of Sustainability, IIT Kanpur, and President of IASTA.
Okay, morning, everyone. I think I'm audible to all of you, correct? And you can see my slides. So yeah, welcome again to this interesting school on aerosol instrumentation. So I will have in next basically 45 minutes, we'll try to introduce you to some of very basic, sampling techniques and some of the instruments which also have become quite commonplace for sampling aerosols or taking them to the laboratory for doing different kind of analysis or understanding their size distribution or other kind of stuff. Yeah. So you see, I'm at IIT Kanpur with two departments, civil and sustainable energy engineering. So this is very kind of a orientation slide, as you see. It's making a lot. So what you see that this is a map, but if you can see, this is a projected map from models from Urban Emission Info that shows that what is the PM 2.5 concentration over India. And many of you are familiar that most of the year round, this is the area which is Gangetic Plain is very heavily polluted. And in fact, other parts of India also has a reasonable amount of PM 2.5. This is for PM 2.5, as you know, particulate matter, which has mass concentration having aerodynamic size greater than, equal to or less than 2.5 micron. And what you also notice that good part of India all along the year is having PM 2.5 greater than the standard set by CPCB as part of National Air Quality Standard. Okay, as you know that there is a standard which our air quality must meet, and that is set for several pollutants, including PM 2.5, PM 10, and some of the gases. So that is one of the major motivation nowadays. Of course, then there are other motivations as well, as we have discussed or heard in the morning, to study PM P 2.5, 10, or total suspended particulate matter. So therefore, if we want to do something about it from the viewpoint of present concerns, or if you want to understand the physics, chemistry, and therefore how aerosols interact with climate, we also want to understand or measure its size, its composition, concentration, and for a variety of reasons we just discussed. And one, again, from the air quality per se point of view, it's quite important that we know what are the sources which are contributing to the PM, what we measure or what we breathe. And the reason being that if you can understand the sources as quickly you can, then definitely you can go after them and you can try to mitigate them. And you see that there are whole range of sources, so we don't have to list it here. You know mostly what sources are, but the real challenge is that what is the relative proportion of these sources which contribute to what you see here in any day or any time of the day or in any season, and which also varies from place to place. And that is what is a very challenging thing. And definitely there, some of the things what you are going to learn will help. And some of the things what you're going to learn will also help you then quantify the aerosol's impact on climate. Some of these things will also help you to decipher how it impacts human health. And the similar properties, if you learn it well, as was mentioned in the morning, will help you to build something, build a technology, or also build either a mechanistic model or maybe a model to understand atmospheric processes or a global model. Okay, so that's why it's quite important that we learn these things well. So since we are going to limit ourselves mainly to some of sampling methods, how do you sample aerosols? Because you know these are very tiny objects and you want to take them from air, collect it, store it, and analyze it. That's one way to do it. Or you just sample it, and while it's being sampled, you can analyze it. Okay. So then broadly, you have two classes based on whether you collect, store, and then analyze. That's one class. Another is that where you do it in the real time, in an online way. And that is what is basically shown here, that you have offline methods where you do not do whatever you want to do. You don't get the outcome, what you wanted to get right there where you sample. So therefore, there is a time lag, and that's why you call it offline. And the other method where what you see that where you get whatever you want to get in real time. Okay, so that is what are the online methods. Of course, this list in both cases are not is not exhaustive. So there can be many more offline methods, and there can be many more online methods. And some of the subsequent lecturers, instructors will be talking of some more methods. And certainly once you know them, I'm sure with subsequent reading, you can learn more about them. Okay. So let's look at some of the advantages and the disadvantages of these two methods. So what you see that, well, you can get very precise mass concentration measured if you collect them and weigh them. And that is what is called as a gravimetric method, where you simply measure the mass. Since the weighing balance are very accurate, so long as you can sample them properly, generally gravimetric method is one of the most standard method. That is why it's used as the reference grade or reference method globally. But the problem is that you cannot apply it if you want to get information as quickly as possible. Okay. And certainly when you don't want only the mass, but you want other variables as well. You want chemical composition, you want sizing, then of course, then several limitations arise. The second problem is that you cannot get these electrodes. So for example, if you want to understand what is the DL or diurnal variation, you will not be able to get it because these samples you collect possibly once or twice daily. So therefore, that kind of short-term variation you cannot get. That's the second problem. The third is, if you have some interest to get some other, as I said, important inferences like source information and many other things, you cannot get those because there will be, of course you can get, but there will be time lag because you store them and then analyze. In that, there is a reasonable time lag of few months to possibly years. Okay. If you look for online method, fortunately for all of these parameters or let's say information, what you get from offline, you can get from online method as well. Be it size, concentration, you can get short-term, these episodic events as well. You also actually reduce this time lag. That where you want to get this source information, you can reduce the time lag significantly. Now, the disadvantages mainly are, one is that they are high cost and they are even higher cost these days, which give you a lot more information. As you know, information is costly. So if you want to increase the amount of information, you must be ready to pay for it. Second is that they also require good amount of resources, both in terms of financial as well as human, to maintain them. So these are the issues with the online instrumentation. Okay, so this is just again kind of we have classified whatever we want to discuss now in next 30 minutes are some of these offline instruments, where one, which is a very rugged instrument where you collect particles in a sampler, okay, which is called high volume. Then there are its variant with little low flow rates are also available. If you want to collect all particles in just one filter with one cutoff, then we call high volume. And then there are other variants where you can have particles collected according to their size. And then these are called like MODI, which is micro orifice uniform deposit impactor, where it is designed to collect particles in various stages. So therefore, in a way, using gravimetry, you can also get the size distribution. Okay, but since flow rate is small, so you need to run it for sufficiently long time to have enough dust collected on the filter. Otherwise, you will not be able to create or construct size distribution, or likely you may not even have enough concentration to weigh them. So that these are the issues. On the other hand, you have these online instruments where you have instrument which gives you particle size distribution in just about sub-micron range, which is the scanning mobility particle sizer. Then if you also want, along with the size, chemical composition, then you use this mass spectrometer, where again there are variants and people from IITM and some others from PRL and others will talk about that in detail. I'm just kind of introducing you here to this subject. And again, Dr. Manish Joshi will discuss a lot about the very basic of these ideas, their basic principle, and then I think subsequent speakers will dwell on that in more detail. And then there is another instrument which can give you online measurements of metal or elemental composition of particles, which is called real-time dust monitor or EXACT. Okay. So these are some of the instruments which we are going to look at it closely. So if you see that how this high volume sampler works, so this is one of the simplest instrument. Now, one or more than probably one manufacturers make that also in India. And reasonably, I think, decent kind of instruments are being made. The only thing when you use it, you have to be clearly be aware of the cutoff curve, what they have used, that whether they have the correct cutoff. Otherwise, sometime when you write publications, that is if your intention, then reviewers may ask that what is the cutoff curve. That's the only thing. But I think they also have a kind of a good cutoff curve already created for that our homemade high volume sampler. Okay. So what is the flow of its working? Very briefly, that from the inlet, air laden with particulate matter comes in. And then depending on the size, there you use the orifice, which can decide what size you want to collect, what size you want to reject. Okay. So what you collect will be, of course, collected on a filter. Okay. And the other will be rejected and the air will go. That is what is shown here using 3 kind of color balls. That one is green, then you have orange, and then you have blue. So what you see that the green guys, right, they just stay here, right? The green guy come here and then just gets stopped. Okay. So because this you want to collect PM 2.5, so you want to reject all others, right? So that is what is happening here. Now, the next one is this orange. So you see orange guy will come and that will impinge on the filter and it will get collected there. And air will simply pass and then finally will go through the exhaust. So not very difficult to see that. Of course, it's little voluminous. If you are having this certainly high volume, there are again, I said that some low flow rate variants are also available. The issue here is that, of course, you need a good housing and you need to maintain it quite well regularly. I'm going to discuss those subsequently as well. Otherwise, I think it's a good instrument to work with. So as I said that this is the curve I was talking about, and what you see that, which is shown that what is the collection efficiency here in percentage with respect to the aerodynamic diameter. Okay, and I suppose that aerodynamic diameter definition will be taught by Dr. Manish Joshi and other instructors. So what you see, the actually ideal curve should be something like that. The way I'm moving my laser, it should come like that. And if you are collecting 2.5, there has to be a sharp fall here, 2.5, and then again it should just coincide with the x-axis. So basically, it means that you should have all the collection as you reach to 2.5 and right or below, and above all are rejected. So that is what that you have a step function that goes like this, all the way up to here, and then like this. Efficiency is 0 as you go above 2.5. But you know that in reality, you cannot make something like this. So anything which can somewhat mimic this step function kind of thing, which is not shown here, I'm showing like this. So closer to that would, of course, will be a nice curve to work with. And you see that most of the standard samplers actually mimic that kind of curve. Okay, they are close to sigmoid and almost like as you are going below 2.5, by the time you reach to maybe what 3 micron, you already see your efficiency has dropped to 5. So 3 micron, you are only collecting 5% of the particle. So it's okay, right? By the time you go to 4, 5, basically you have come to 0. If you look here, you go to 2.5, you have 50. That is how we are deciding T50. That is the design criteria for this, right? So, and the moment you go to 2, you see it has risen to 80%. So 2 micron you are collecting with 80% efficiency. So it's quite good. Now, one thing is there, what you must be aware of, that you must have the measurement of pressure and temperature. That happens, that there are sensors in this sampler, fortunately. So you must correct the flow. That's one thing. And second, that how, if you are interested, how do we actually get this design criteria? This is the sole thing. This is the soul of the sampler principle. That D50 is basically given by this expression. Okay, where you see that again, then this Stokes number is a non-dimensional number that I think most of you probably would know. So again, the W, which is the diameter of the orifice you are using. Okay, and that is basically going to determine how you are going to design a sampler. So basically D50 and all others, if you look here, this is a parameter or property of air. And these are some standard thing like slip correction factor. And this is, of course, is a flow rate. That's also important. You are monitoring that as well. So Stokes number and CC are connected with aerosol property. This is a air related property. And then this W is the orifice width or diameter. Okay, and Q is the flow rate. So primarily, if you see that, it's a combination of the particles property and the flow property, and also the sampler design criteria. So that is how we basically create this D50. So you work with the orifice and you look at the particle size, and accordingly, you by varying it, you can arrive at a D50. Okay. So what kind of precautions we must take while sampling with high volume sampler? You must prepare first that the filter must be clean. That means you take all the precautions to keep it clean, because you are collecting particles which are of size 2.5 micron or less. So you can't see with your naked eye, as you all know. The mass you are collecting would be from few tenths of microgram to at the most few hundreds of microgram. So that also is a factor of 10 to 3 to 10 to 2 lesser than gram. So that's another very important thing, that if you lose or you add, then you can have sampling artifact or inaccurate sampling. So therefore, you must have clean workspace. You should use gloves, etc. And then while doing the transport, you have these, again, care we must take while taking this work forward. So transporting, how do you attach to it? And you secure all the belts and everything, right? Then what it says that you have to load the filter onto this cartridge, which is shown here. So you see that this is your cartridge, you will take it out. Inside, you have loaded the filter, then you put the window, then you tighten these screws. Okay, that is how you should do it. And then one important thing, of course, you follow all these. So this is all written there. I'm not going to go over that. One very important thing is that during the sampling period, you must look at the overall flow rate, because if the flow rate deviates more than plus minus 5 to 10% of what is mentioned here, okay, which was mentioned something like 1.13 meter cube per minute, which is just about 1100 liter per minute. That's why it's a high volume sample. So if it deviates a lot, then you would find that this complete red, this inner circle, will have some patches. So that is what you must look at it. Okay. So that is, if all this goes well, then of course, sampling complete. Then you again open this, take away the filters properly, take to the lab, store it in a refrigerated condition. Generally, you keep it at few degrees Celsius, because otherwise lots of volatile and other thing can be re-volatilized from filter into there. So you lose mass for possibly organics or sulfate, nitrate, and other stuff. Okay. So these are what you see, that it is a clean filter. And once you have sampled at a polluted place, that is what it looks like. Okay. So that is what you do. Either you do twice daily, then of course you run the sampler for 12 hours, then you switch off, remove the filter, and then you unload, and then finally you keep it in the laboratory for chemical analysis. So this is the work which I'm showing you one example that some reasonable amount of sampling we conducted at 4 or 5 locations from Kanpur to all the way up to Hisar in Haryana in the winters and spring of 2018. And we had a good number of filters collected from all these places. And one of my students, he looked into the diurnal as well as seasonal variation of elemental and organic carbon from these 5 sites. And then some other work was also, as a follow-up, was done by another student of mine. And she looked more into sources and then connecting with the health, but that I'm not showing. So you see that there are some, in fact, even with some things like this, if you collect it, of course, you need to have enough filters. That is where the time, goes. So for example, here, in order to collect these twice daily filters for 6 months, you have to have a lot of, manual effort that goes into that, and then, storing it and all that. But if you do it well, of course, results are quite good, rewarding, interesting. What you see that these are the black carbon, day and night. This is for what location? This first one is for Hisar. Yeah, it's so small I can't see it. Thanks. Your eyes are good. And then for other locations, right? So you see that there is some diurnal variation, then there are seasonal variation, but that's not so important. It's just to show you that once you bring it, of course, you can expose it to ECOC analyzer and many other things. As I said, that all those offline chemical techniques. Okay. And then there are many other things you could possibly do here. You can then do this ECOC analyzer can give you elemental and organic carbon. You can run to this ICP-MS, you can get metals, as some of you know. You can get polyaromatic hydrocarbons, which are also very important in deciphering sources through GCMS. Then other ions you can get from ion chromatography. So there is this example that on the same filter, same student did to get the metal. An idea here was to look into that the overall accuracy of the real-time metal monitor vis-a-vis that metal we analyze based on filter collection and exposed to ion chromatography. Okay, and we had reasonably good agreement. That's what a paper we got into atmospheric measurement technique. So basically, if you do it well, then certainly you can get some good result. One other caveat I should have added that generally with these techniques offline, you don't get sufficient information about organics. You get the bulk organic, which I showed earlier, but many organic molecules, as you know, that organics can be there in a variety of ways, and you know that organic families. So there's so many. These offline techniques actually do not give you enough differentiation, enough granular level information about organic. So if you're looking for organic related sources, of course, the technique doesn't give you very good information. Okay. Now let's switch our attention to another technique, which is a condensation particle counter, which can be operated as a stand-alone instrument where you just want to count particles less than a micron precisely, very precisely, only counting. Or it can work in conjunction with some other, add-ons, which I'll be showing in subsequent slides to get the size distribution. So then it becomes part of scanning mobility particle size. So principle is very simple. I have not put the equations of particle nucleation here. I'm sure somebody, Dr. Joshi or somebody will talk about that. That idea is very simple, that particles come with air inside the instrument, and you use some kind of a condensing material, in this case, butanol, because butanol has a very high vapor pressure, okay, very volatile kind of, easily, condensable organic it is. So if you keep these butanol wetted, quick inside from which the butanol vapor are coming out. And as a particle moves, the butanol goes and condenses on that very, very smoothly or in a very simple way. Simple means in a very, what I should say, in a very, much better than water. Let's put it that way. Although these days there are water-based CPC also have come around because they have now advanced the technique. But for long, butanol was the choice vapor to use for condensation. Now, idea is that because you want to count everything below 1 micron, that means you also want to count particles as small as 3 nanometer, or sometimes you can stretch to 2 nanometer. So these are very, very small particles. So it is quite important that you grow them in a very short time, because the time is crucial. Your instrument is not very big. So the grown particle must, while traveling, pass through the laser. So there is a limited time you have. Therefore, the growth must happen in an expeditious way, fast. So that is why butanol, right? So then this very small particle, 1 nanometer, 2 nanometer, can grow fast. And then after growth, they can be just passed through a laser. And the laser will continuously be firing laser. And then that signal will be, of course, arrested. And that will tell you 1 particle or 2 particle, and accordingly you measure it. So you get only total measurement, that every volume, what you have sampled, how many total number of particles are there, less than micron or whatever is the impactor you use. Because here also you must use impactor to throw away, reject the particles you don't want to measure. Okay. Now this is about CPC. As I said, the theory of nucleation which combines Kelvin and Raoult's law. I'm sure you must have been taught. If not, you can look at in the books. Basically, find the right use in this instrument. Okay. Now, as I said, that if you couple that with a DMA, which is a differential mobility analyzer, then what you can do, that you can do counting, but in various sizes. So that means that you can segregate it in different sizes and can count. So the DMA does this segregation based on one important parameter, which is called electrical mobility. Okay, so this instrument actually works on electrical mobility principle, which is basically the velocity of a particle when it is charged, okay, in a unit electric field. So particles are generally electrically charged. In this case, of course, you give them a designate charge. Okay, that is why if you see somewhere it says that you put it through a neutralizer. Okay, so neutralizer here is used basically for giving you or giving the particle population a known charge distribution. Okay, and there is some radioactive source, and through that you kind of provide a charge distribution on that. So once you give them the charge, and then you keep this central rod inside this DMA. So you see, this is the long DMA. We call it long because there is another version of that, which we'll see in the next slide, is a short DMA. So the long DMA, you see, you keep it at certain voltage, okay, and outer, etc., will be kept as 0. So you create an electric field between these two. And then your polydispersed aerosol, because you are wherever you are measuring, this aerosol always has a size distribution ranging from whatever, few nanometer, few tens of nanometer to few micron. So certainly first you want to use an impactor somewhere here, which can again screen particles, let's say greater than 900 nanometer or 1 micron. That is what SMPS has, this range. And then the particles less than a micron, say, then they come with a distribution inside, okay? And they already, you have passed them through this neutralizer. So they have been given some kind of a known charge distribution. So that they have tuned it, that he provides a known charge distribution. So you already know in every size, what's the fraction is having neutral charges, so 0 charge. What's the fraction has this many negative charge and that exactly same positive charge. So the whole distribution is known a priori. Otherwise, you will not be able to get the subsequent information from there. So that's a very crucial thing. And all that detail, I think you can read in the book. So once you have done that, now this is basically the voltage on the central rod is worked out in a way so that particles of one mobility, electrical mobility, can go out from here. Okay. And now electrical mobility, as I said, is a function of electric field. Well, it's per unit electric field, I'm sorry. So it's mainly depending on two things, particle size and particle charge. So more charge you'll give, of course, particle will shoot faster. Okay. If it's larger in size, it will slow down. So this basically based on that, and electric field always can make it, go swiftly. So now you are able to create kind of a monodisperse flow of aerosols from here by working with the known charge distribution on particles and the voltages. You get that, and then there is some mathematical inversion is involved. Using that, you can kind of create the whole your size information, and then downstream you have the CPC, which is doing the counting. So this way you can count particles in every size bin, and therefore you can construct a size distribution. Okay, that is what is the idea in the case of long DMA we have. Now, if you look in the short DMA, so this actually works for most of the instruments which are available currently for scientific purposes, works in the range of 15 to 16 nanometer to 890 or 900 nanometers. Sometimes some instruments have a range of 1 micron. If you work with short DMA, principle remains quite much the same. But in short DMA, the difference being that you get the size range from 4 or 3 nanometer to about 150 nanometer. So there is an overlapping range, and then there is a software which actually you would know if you have both nano and long DMA working side by side, running side by side, then you can, taking the two distribution, you can merge them. That's called the merging software. So it will look into that overlapping range and it will try to merge it in a proper way. So that there is a smooth distribution that comes out, giving you the full size distribution of particles from 3-4 nanometer to 900 nanometer. And for that range, it is one of the possibly best instrument to work with, right? The other option is that, as I said, that when you collect particles in different at different plates using various orifices, which is something like Moody we have seen before. Okay, right? So this is what you have this full instrument that looks like this. I'm sure you will have this for demonstration here. This is the TSI one. You might have either GRIM or TSI, whatever is there. The actual working principle, to my knowledge, does not differ so much. Okay. And this is just to give you the complete flow diagram at how this works. So this is not very important. You can just go through. Right. So just to give you the complete flow of this, you have the impactor to segregate the particles you want to only sample. So less than 2.5, actually it should be less than 1 micron essentially. Then the neutralizer, which gives a known charge distribution. Then you have a DMA, which classify particles, either it will be nano or long. And then you have the condensation particle counter, which counts the particle. Okay, so this is how it all works. And then once you start working, you will find that it actually gives quite a few diagnostics all the time. So this is what is important. Either you look at it or you create some program so that it is shown to you on your computer. You can also, as you know, can look it in these things through the team viewer these days, but it is important to watch it because the moment some alarm comes, like in this case, what is shown in this red box, that if you are sampling while the alarm has been triggered, then you will find that your distribution is no longer trustworthy. So these are quite important that you look. There are several like that of course will be shown to you during the actual demonstration. So this is one thing which many people do. We also have done it, that if you measure it for a long time, then there is a possibility that you capture these, what is called that nanoparticle formation, nucleation, what is known as, or its growth. And these are very interesting events, because if that happens, it shows that such kind of pollution events are happening at a larger regional, stage. And this is what is one data is shown by one of my students after sampling it in Lucknow. And what you notice that if you see that this is what is called it's a 3D curve. Of course, you are plotting size distribution as a function of time. It has some name, I'm forgetting that. So you have this size distribution here, right? That is shown by the color. So more and more pinkish or reddish color, that means you have more concentration. And then on x-axis, you have dates. So every day, how it looks like. And then if you go in the y, that shows the particle size. Okay, so as you go from year to year, particle size is increasing. So that means particle size are growing. Okay, so that is what, like, when this is encircled here, it shows that there is a prolonged growth. And that once you notice something like that, then you start looking into that, and then you test it against several kind of guidelines. There are many to really see that whether it's a nucleation event or it's a growth, and then you can do more analysis into that. Okay. So this is what one work we did with one of my students in Delhi, where what you can also do, that this instrument allows you to compute growth rate in every size bin. Okay, that requires some other computations, some other models to be developed, but some of these models are available online. So all is required that you should be aware how to use it or modify it to your needs. That is what you see, that the growth rates have been computed for particles sampled over Delhi from SMPS at 3 sites for whole year. Okay, and we are only showing for winter. So you see, you can calculate these growth rates for greater than 100 nanometer or 60 to 100, and likewise you can go all the way up to 20 to 25 to 40. So these growth rates are giving you some idea that particles are growing 5, 10, 15 nanometer every hour, and these are quite accurate. These doesn't have large error, but they are done very well. And then you can look that what's the growth rate, what has been reported, and where our growth rates lie. Okay, and that can give you lots of insight. Then you can also compute these condensation sink, which tells you about pre-existing particle surface area which is present. That gives you an indication about how much vapor sink is already available in the atmosphere. So more the sink is, lesser the nucleation or growth will occur. Okay, or certainly less nucleation will occur. So that is, you can also correlate it with growth, and you can see where this particular event stands with respect to other such events which are shown from global measurements. Okay. And then you can, if you have also some chemical data available, then you can look into the chemical information, which was fortunately available that time, and can give you some idea that what was driving that growth rate. Okay. So if you have like some information about this particular tracer, which can be traced to biomass burning. And if you have this measurement, you can see when the growth was happening, whether this tracer was showing some peculiar behavior. And if so, then you can certainly infer that possibly this growth was led by some kind of biomass burning. Okay. Now, next is this Moody micro orifice uniform deposition impactors. So this, as I said, that if you are interested in doing particle collection in various size ranges, which I said that you can do it with SMPS. But if you are doing in laboratory or indoor, and where sometime temperature, etc., could be high, where instruments like SMPS, what we just showed, have some very stringent conditions for operational range. That is, the temperature goes above 35 or 40, then instruments actually start complaining. So you have to have AC and all those things always be there in order for a smooth functioning of the instrument. Now, these kind of moody kind of instruments are quite stable and rugged, that they can be operational for even 50, 60 kind of Celsius, not very high, but reasonably high. Second, as I said that if you are not very much interested in looking on diurnal, dial or short-term episode, you are okay that you have one sample collected every day and many days you have collected, and then you want to bring them, analyze them, then definitely, as I said, because gravimetric technique being accurate, it is going to give you reasonably good information, and then you can also do the chemical analysis, and then you can get more data. So all these, what happens that at every basically stage, you have orifices, and each of these orifices are basically designed for exactly like the curve I showed earlier, the D50. And D50 actually varies from largest to smallest particle. So in that way, you can collect particle from maybe 4 to 10 micron, then 3 to 4, and likewise you can go all the way up to less than 50 or 100 nanometer, depending on how many stages you want to use. Okay, so that way you can really have a whole size distribution constructed, and then you can do some other things. Okay. Then online version of this MODI, where you get the online size resolved chemical speciation of particle, is your mass spectrometer, which I'm sure you will be seeing here, either here and at Mahabaleshwaram, or at both places. I think ITM has this mass spectrometer. So what you see that this instrument actually is integration of many small instruments, as you will see. So you have a particle inlet, that particle enters from there. Then you have a lens, which is aerodynamic lens. So basically they are like progressively changing diameter orifices, which tries to make that aerosol, which are coming with the air, more and more concentrated. Okay. That's the idea that you have a very concentrated thin aerosol beam that enters into the main chamber, which is your main chamber. And then use a chopper, which moves in reverse direction, okay, just to chop the part of beam for some reason, we'll see later. Then you have a PTOF, which if you turn that on, then it gives you information also about the sizes. And then, of course, that you have a high temperature plate, which vaporize. And then you use a medium ionizing source to ionize the molecules, because what you get from here is mostly molecules. And if you now bombard it with some electron, then they become ion. And then you basically measure these ion in two modes. Okay, one is called W and V. V depending on what is your need at hand. So you see, you start with the sampling inlet. Then I just said that it goes into the aerodynamic lens. And then there is a supersonic expansion because you have atmospheric pressure here, because you are sampling in atmosphere or room. So virtually it is same, 1 bar or 1.01 bar. And inside then you create a vacuum, which is of 10 to -4 or 10 to -6 bar. So that most of the air you want to keep outside, because your interest is only to basically measure these aerosols converted into ion. Because if lots of air will come, with air molecules will come, and they will then basically create problem with your signal. Okay, so that's why you have suddenly brought the air brought the pressure down by 10 to 6 to 10 to 7. Okay, as much you can, right? So that is what is done. So now, because very high pressure to very low pressure, so you see that now these ions will simply, like will go with the rocket speed. Zoom. And then that chopper helps you to do sizing, and then you ionize, you get ion, and you get the mass spectra. So this is what this instrument looks like. All these things are shown, which you can see, and you will of course see it in person by looking at this instrument. And then there are many diagnostics which you must look at. Some of them I have just shown here. That once you see this, you'll be able to relate to that. That what are those range of parameters which instrument must be operating within that. Okay, and you would soon learn that. And certainly this requires a lot of attention that you have to have very attentive about when you are running this instrument, because small mistakes can not only create issues with your data, but can also harm the instrument itself, which is very expensive instrument. So therefore you have to be very careful. And then as you go along, I'm sure you will learn about two softwares. That there are two important software. Besides, you must also learn the IGOR, because most of the analysis and the analysis tools which are available in public domain are in IGOR. So if you learn IGOR, it definitely helps. So one is that your Squirrel, which if you want to do analysis for UMR spectra, that is the ion mass spectra is plotted in a unit change in the mass of the ion. That 1, then 2, 3, 4, 5, right? But we all know that in reality, there is a continuous range. We have decided that hydrogen has 1, right? But between hydrogen and helium, there might be other things. But for our purpose, we have made it like that. So there, one after one, there could be 1.01. In fact, there could be 1.0001, etc. But it's better that if you want more signatures of the chemical constituents, it's better to work with HR. So therefore, the other option is that you work with HR. So for example, you see in HR mode, you can get 27.9949. That also could be an ion. But here in UMR, when you are doing a quick analysis, then of course you are ignoring it and you are clubbing these two into one mass, which is 29 or 28, right? So that HR, you use Pika, and for UMR, you use Squirrel. Okay, all that I'm sure you will be shown. So once you have done all that, then of course you get that you can get, in fact, one thing I have forgotten to include here is that there are 2-3 calibration you have to do before. That's totally, I think, forgotten. I hope that they will show it. That you have to do ionization efficiency. That's very important, that the moment you shift your instrument from one to another location, you have to do IE calibration. That's very, very important. Ionization efficiency calibration. Second is that if you do some long range, let's say transportation, that is, let's say from ITM you take to even, let's say in Pune city. So that has involved some transportation, some movement on the road, then you do a lens calibration. That lens also can be misadjusted. So you have to do that. And third is about size. So these three, but size we don't do very often. IE we do quite regularly. Lens we do if we have to do some long-term shifting. So these three calibration you must learn. And one of them, in fact, two of them, both IE and size, you require an SFPS. So this instrument has a prerequisite in terms of another instrument, that is SMPS. And that has also one other required instrument you should have, which you're going to learn, by the way, is the atomizer. So you should also have atomizer so that you can generate particles. So you generate either sodium chloride, common salt, or sodium sulfate. Either of that you generate, ammonium sulfate. And with that, then you do this kind of calibration. So once you have that, then of course you see at every minute or 10-minute resolution, you can construct these species like organic and all those, what is shown here. And then even if there's a burning going on at a very short time scale, let's say, at this particular day, there was a burning that from 3 to 4 inside IIT campus, the instrument was switched, kept running, and you can pick it up. Then you can actually average it and you can create these kind of pies, and you can do a lot more, as I'm going to show it very quickly. That then you can apply these kind of software where you see that all these time series, which can be these all time series for each of these organics or sulfate, nitrate, chloride, and blah, blah, can be clubbed to make this matrix. And then you can invert this matrix. This becomes a matrix problem. That is AX is equal to B. That means it basically gives you a big set of linear equations. So it's a whole system of linear equations, very big. And there are many ways to solve that. That is what is shown here, that you are getting that a concentration which you are sampling is equal to sum of these two important, parameters which are mentioned here. One is what it says that G, which is a contribution of a factor. What is factor? A source. So when you sample, let's say sulfate, then sulfate would have contribution, and sulfate, let's say at particular time now, 12 noon. So sulfate now what you're sampling, let's say inside IITM, will have contribution from many sources. If there is still some little sulfur present in the fuel, I know it's very little sulfur these days we have in the new ultra modern vehicle, but there are some old vehicles which are also flying. So some sulfate will come from that. Then if you have a power plant nearby, thermal power plant, some sulfur can come from that, and many other sources. So it says that what is the relative contribution? And then there is a F, which says that concentration of species in factor profile. So that particular source, what is the fraction of this species? That you combine these two, that plus an error. Because when you are getting this solution, there is always some error. And what you want to do, you want to minimize this error. That is what every technique does that. Okay. So there are two techniques which are very well used. One is positive matrix factorization on the left here. Another is a slightly improved technique which is called multi-engine 2. And the strength for these two comparative strengths are both mentioned here. Okay. So that's up to you what you want to do. So this is what you can also do some other things here. If you see that how this mass spectra looks like. So you can have a mass spectra of HR, which gives you good strength up to 100 AMU, M by Z, basically. And then in UMR, you can go up to 300. And why do you choose UMR? Because many organic species actually have a signature in large mass by charge in. Okay, so that's why it's good to work with a combined spectrum. Then there you will be able to get the source information very well. Okay, that is what is done here over Delhi. That at 3 locations, we are able to get very good information about the sources and their relative contribution using this technique. You can do a lot more. I mean, if you now combine, generally we all do this on organics. For organic, it's a very good instrument. But now if you combine organic and inorganic, then you can get some even additional information, what is shown in this paper, that you can understand that for particular haze time, what is the relative concentration of, let's say, a couple of these factors, which are sources. This is like one kind of oxygenated organic aerosol, okay, which is less volatile. That means it has a preferential tendency to be in the aerosol phase, less volatile, correct? Then you have biomass burning oxygenated, a biomass burning organic aerosol. This is a kind of organic aerosol, but it is coming from biomass burning. We have been able to recognize by looking at that mass spectra. And then what we are looking at? We are looking at agriculture burning period, AGB, and rest period. And you see there are clear differences which are coming out after 2 to 3 months of sampling at 2 important locations in Delhi. One is IITM, their own institute has a lab there in Delhi, another at IIT Delhi. So there are many such things, of course, you can do if you analyze it well. So finally, I think this is my last slide, where this instrument is now relatively new. So generally, again, the practice was to collect particles on filter and then analyze it using, as I said in the very beginning, using ICP-MS or some other techniques like AAS to get elemental or metal information. Now, as I said that if you require these information in a real-time manner, then of course you have to use something which gives you this kind of data. So this is what is an instrument which is called dust monitor, or short form is used as EXACT. Okay, so this is basically XRF, which many of you must have heard about, and that X-ray fluorescence. It uses that, but of course its instrument, it could be made mobile. That's all this instrument does. So what it does, that for 1 or 2, 3 elements, it calibrate, and then for others, it just applies that calibration factor. But I said that we try to compare data obtained from this and data obtained from the offline technique, and we found that for a range of elements, quite a big range of elements, the correlation is quite strong and error is very little. But then there are some elements for which, of course, the correlation is not so good. So that's kind of work few people only have done. And you could look into that to evaluate overall accuracy of this instrument for getting the elemental information. Okay. So this is what you can get. For example, a particular element, you can get the complete time series. And then, in fact, it gives you, in principle, about 35 to 40 metals in real time. But good, I mean, reasonable amount, which can really impact the source profile, would be only about 20 to 25 metals. So many metal information you get, which itself can help you to get decent information about sources. So this, for example, we have done in this paper that if you look, that we using only elemental data, we could classify into various sources. That, for example, there is something called chlorine rich, which could be because of combustion of municipal waste or industrial waste. And for example, you can also get copper rich. That can give you whether there is a smelter close by. And so many such things you can. Sulfur rich, that can indicate that whether there is some power plant. And if you look now also with this lead, then you can again go deeper. So lots of very interesting information you can get, right? What's all mentioned here. And then you can combine this, of course, meteorology, which other people will talk in more detail, to find out that what is the source location. So if this is the sampling, this black dot is sampling. So by combining the back trajectory, or basically the wind speed and direction, if you have that at a larger domain available, then you can combine that time series, that is the wind speed and direction, with this time series to give you a good idea of the relative source strength, that how they are spread out. So for example, in this case, you see the sources are mostly coming from here. But in this case, you see it is coming from both sides. And in this case, mostly it's coming all from this side, mostly to Delhi. That sulfur is coming from Uttar Pradesh. And in fact, you could go and see these slides, you will have it. You will find that there is just a big power plant, 150, 160 kilometers in this direction from Delhi in Dadri, in Uttar Pradesh. So it can give you really very good intuitive information. Okay. So this is all I have to say. If you have any question, quickly you can address, and otherwise we'll stop it. Thank you.
To how you decide which filter to use, like according to campaign, like quartz, Teflon, how you decide, like what is the basis of deciding the?
Yeah, so one thing is very, I think what I remember, of course, it's long time I have done it, but I think that, for example, if you definitely want, let's say, silicon, so you don't use quartz because quartz will have silicon, right? So that's no. If you want, let's say, carbon, elemental carbon or organic carbon, right? Then Teflon, generally we don't use, right? Nowadays, I think they have started using, you will not use. So depending on now in the raw filter, blank filter, which element has, prominence in that, definitely then that kind of elemental information you are not looking from that filter. So that is one thing. Then second, then it also becomes important that what kind of sampler you are using, right? So many times for low volume, high volume, then there are some other recommendation. The third thing is that nowadays they have samplers where you can simultaneously sample both PM10 and 2.5. So then again, what choice you use to have, right, that all elemental information available to you without compromising with these issues. So, but this is not a very big deal. I mean, you can work it out.
Sir, what is the difference between W mode and V mode other than the path length?
So W mode and V mode, actually, one of them give you more resolution. If I recall correctly, I think Dr. Pandit Rai is here, he can tell more, but I think one because it takes longer time, it resolves into high HR and other don't give you the HR. But you can look into the paper just to confirm that.
Sir, regarding the offline measurements, like what is the optimum time like filter should be, like as you said about filter degradations. So while if you are doing campaign mode, so what is the optimum time that we have to chemically characterize the filters?
That means storage time in the lab?
Yes, storage.
So storage, if you have stored it at temperature below 2, 3 something degrees, what they say, then you can store it for easily for a year, 1.5 years. And generally people do, they have long campaigns. Then they don't get time to analyze it in batches, rather they wait that all filters come in. So a year, 1.5 years. I mean, a year is a, let's say, good time. But you can also do, people sometimes store it in deep freezer. If you have deeply refrigerated it, if you have deep refrigerated it, then you can do it even after a year, not a problem.
Your question about NT-AAI impacted. So what should be the flow rate for that? Like for high volume, the sampler's flow rate should be 16.67 as per my knowledge. So is there any flow rate?
Moody we have used a lot, but it says that 30 liters per minute.
Okay.
That's why I think if you want the particles collection in all stages, then you have to run it for a long time because the flow rate you see is 30. The other one had 1100 liter. So difference is large. And then whatever you are collecting, that also is getting segregated in various, right? So if you are in a very close to proximity to a source region, then of course, even with a smaller time sampling, it could do. But if you are some other places, maybe. So that couple of days we just run and you look at that how much you are weighing, and then accordingly you come to the sampling, that sampling time, because flow rate is fixed. Flow rate you can't change, right? So sampling time accordingly you adjust, yes. Okay.
Sir, just a question on that long DMA. So how is the particle decided that how much charge it will get? Like if a particle is smaller, it is getting small charge. Bigger particles getting big charge. Will the chemical composition will have some interference on the charging of the particles?
Chemical composition, size, both basically decide, but there are some well-known charge distribution, right? That people know. Like Boltzmann, you may have heard. I think Manish will talk about that, right? Charge. There is a full discussion on that. Then there is a Gaussian. So mainly that follows actually two things. One is the particle size. Larger the size, can have larger charge, you can know. Second is the important parameter, which is the ratio of the ion concentration and its mobility. Product of ion concentration and mobility for positive and negative. That ratio actually determines how the charge will be distributed and the particle size. Now, the known charge distribution expressions are very well known. So now you can play with that radioactive or other source, whatever, ionizer, to basically see that whether the particles are attaining their charge distribution. And that is what they do in SLPS, right? You have a fixed charge distribution, correct? Yeah.
Okay. Thank you, sir.
Anything else? Okay, thank you.
Thank you, Professor Tripathi, for the lecture. Now we will proceed for the second lecture. The second lecture is by Dr. Manish Joshi. He is a secretary of IITM present. Dr. Joshi works as an aerosol scientist in the Radiological Physics and Advisory Division of Bhabha Atomic Research Center, Mumbai. He has expertise in instrumentation, aerosol measurements, and aerosol modeling. Please welcome Dr. Manish Joshi.
Okay, good afternoon. So we have already seen now a bit on aerosol instrumentation in Professor Tripathi's lecture. I will be now going back to some basics which are related to the instrumentation lecture which you will be having in your rest of the classes. These are very fundamental things, so maybe most of the things you may be knowing. So I will keep it in a slightly interactive manner so that some new things should be known to you as well. And some things if you are knowing, there is no harm. So we will be having a complete story to finish the thing so that when we have the rest of the hands-on session, you have the basic ready with you, which will be important for you to know. So in that sense, now the first term, in fact, it is now I am already, you have seen the last lecture, so where you have already discussed about the advanced things. So I am now going back to preliminary things of aerosol science and technology, and definition is the first thing, right? So you all know that when I say about aerosol, it is the suspension of solid and liquid particles, solid or liquid particles in air, right? But when we just understand this definition like this, when we say it is a suspension, so this suspension also has a time history involved with its definition. So this time history means when we say suspension, so it is a meta-stable suspension, but it means that it is basically suspended for a practical purpose of time. So you may be generating some aerosols in a closed chamber, which may not remain airborne for a considerable amount of time. So will you call them as aerosol or not? That is the question, right? So when I say now aerosol, when I say aerosols, so the stability depends on how much time you want them to be stable. A particle of 10 or 50, 20 micrometer particle size will no longer remain stable for a considerable amount of time. But if that time is sufficient for your experiment to be performed, then that will be treated as aerosol, right? Similarly, in atmosphere, if you are having some spectrum, you are having different sizes. So if they are there for a considerable amount of time, they will also be treated as aerosol, right? So there are many examples, you know that. And when we talk about now size spectrum, or what are the sizes we are having for some particles to be treated as aerosols. So we have the upper threshold 50 or 100 micrometer roughly, and there is a lower threshold which is generally 1 nanometer, right? You must be having some idea why this 100 micrometer, right? So the test definition itself gave the answer to you, right? So when I said metastable means it has to remain in air for a considerable amount of time. That means that if you are having 100 micrometer particle after my lecture, you will be having that calculation in mind as well. You can easily calculate how much, what will be the settling velocity for a 100 micrometer particle, and you will easily know that it will be just a matter of second that it will fall to ground, right? So in that second duration, you will not be able to perform any experiment. That means that it will be not be called as aerosol. That is the practical reason we have upper threshold of 100 micrometer when we define the aerosol particles, right? While there is another now threshold at the lower spectrum, which is 1 nanometer, right? And you must be knowing the reason for that as well. I don't know. But basically, when we say 1 nanometer, it is just distinguishing it from the air mixture. So when we say suspension of particles in air, air is already present. So air is also a mixture of gases. So there are many air molecules which are already existing in your air, right? Nitrogen is there, oxygen is there, argon is there, water vapor is also there. So now what makes it different when we are having some particle suspended in the same medium? So when we talk about aerosol particle, if some particle is having size lesser than 1 nanometer, you do not need any different aerosol dynamic principles to understand that. Kinetic theory of gas can be applied for even that particle. It will be treated like an air mixture. So when the size is distinctly different from the molecular size, which is basically lesser than the 0.1 nanometer for air, then that spectrum or the suspension will be called as aerosol particle, because then you will be requiring not only kinetic theory of gas, but something else as well to understand its dynamics. Stokes drag law will come into picture, and everything then will be governed by the drag law and the follow-up equations, right? So that is the reason we are having another bound at the lower spectrum, which is basically 1 nanometer. This is that spectrum. We will be having now so many examples when we talk about now aerosols from 1 nanometer up to 100 micrometer. And now you can have some exercises among yourself later on. We can have examples of aerosols in different size spectrums, right? So if I talk about the logarithmic scale, so you are having now 1 to 10 nanometer, 10 to 100 nanometer, 100 to 1000 nanometer. You can always think about hundreds, maybe 20s, 30s, at least those examples which will be having their sizes in this range, this range, this range, this range. So you can take this challenge, you are sitting here itself, and then you can think about each example in these size ranges, and the examples should be different from the adjacent people who are sitting near you, right? So you should be thinking about 3 examples so you 1, 2, 3, 4, 5 examples you need. But when you are talking about now 2 persons who are sitting close to you, so there will be 15 aerosol particle examples, right? Which will be at least covering the entire range when I am talking about right from 1 nanometer up to roughly 100 micrometer, right? So this is that spectrum which we will be talking about, and Professor Tripathi has already explained that we have a range of instruments to measure the characteristics of these aerosol particles. Now, the role of aerosol is already clear during inauguration session, and in our follow-up lecture, we already discussed that it is the part and parcel of quality of life, right? So we only will be knowing when the air is good or bad, right? If we understand the behavior of the particles which are present in the air. In the same way, we know that these aerosol particles are impacting atmospheric system at local as well as global scale, right? You are very well aware about the visibility effects. You know that they are acting as the cloud seeds, so rains are affected by that. You are aware about the cooling or warming effect. You also are aware about the climate change implications, right? So knowing aerosol properties, measuring them, understanding their behavior is critical to understand how it impacts atmospheric system at local as well as global scale. Now, we also know that right from our household up to very advanced application, we have so many utilization of aerosol principles, right? Perfumes, spray, and up to drug delivery, we have so many examples. And we also know that now when we talk about this aerosol particles, this is that invisible companion having its own characteristic behavior. Invisible word I use because we don't know right now when we talk about dust particles, which are basically silicon dioxide particles suspended in air. We know that we are able to see that because their size is in micrometer, but there are a range of examples which are lesser than 1 micrometer, which you are not seeing. However, our aim via aerosol instrumentation classes is to get a feel of that, or in fact, to get an eye to see those particles. particles, right? So we want to see those particles, we want to predict their characteristics, we want to measure those characteristics. In the same way, what is that behavior now we are looking for is the ideal, or what I can say is the theme of this lecture now. So now coming to the next, aerosol characteristics. When we say, before moving to aerosol characteristics, if we just in nutshell, if we just describe what is going to happen now when we know aerosol characteristics, first of all, the life and fate of aerosols depends on their characteristics. Even during their generation phase, you will be learning about now nebulizers. There are some other generators as well. So when we generate aerosol particles, so what kind of characteristics we need, right, will be decided by the technology, or will be decided by the instrument what you want to generate those particles. Once they are generated, they will get evolved. They will not remain as the similar size particles. They will be interacting with each other. So their size spectrum will be continuously evolving. So that evolution, generation and deposition phase will be modified continuously on the basis of the characteristics what we are having on hand, right? Similarly, now when we talk about the measurement of characteristics, it is required because we want to predict the behavior. What will be going to happen with these particles? Whether they will deposit inside our lung at the designated place or not, right? What is the toxicity of the particles? It will only be known when you know its size. Similarly, if you know the chemical composition, you will be beforehand knowing the toxicity of particles. So the characteristics, if you are talking about, those characteristics will be deciding the behavior of those aerosol particles. And now the aim is to measure or just to simulate or predict these characteristics, and different instruments are available. You will be seeing that a range of instruments we are having in our workshop itself, and these all instruments are measuring different characteristics, even for the same characteristics, right? You will be having different techniques. Your same instrument you cannot use for the entire spectrum. Size is the classic example, right? You know very well that when we are talking about the size of aerosol particle, it is varying from 1 nanometer up to 100 micrometer. You cannot use the same instrument or same technique to measure the entire size spectrum. That's the complication. That is the thing what you should now realize in your workshop classes or demonstration classes. Now coming to the next part, when we talk about the size of the aerosol particle, I already mentioned that it is the most important characteristic, because this is that characteristics due to which it is going to be deposited inside your lung. Ultimately, whatever is in the atmosphere in your lab, the toxicity or the effect comes when you are inhaling those particles. And the inhalable fraction where it is going to get deposited, whether it will be stopped in the upper respiratory tract, or it will go deeper to your AI tract, which is the deep part of our lung, from where the clearance is tougher. It will be decided by what is its size. Similarly, this size generally is expressed in diameter or radius. When I say now, I mentioned 1 nanometer of particle, right? So that time I just mentioned that it is the diameter of the particle which we are referring to, right? So some maybe in some example, particularly in Nuttall number, you will be seeing that they will be using radius. So it is just convention. Diameter and radius are closely linked. The size of particles could be same. Generally, practically, it will not be very easy. Even if you are generating particles, you will not be able to generate all particles of same size, whatever source you take. So whenever we say even monodispersed particle, they will have a very small dispersion. But that dispersion will be very, very small. But when we talk about the actual size spectrum, the size spectrum is polydispersed in nature. It will be having all possible sizes. A spectrum will be there. And when there is a spectrum, then you will have to understand the statistics of the spectrum as well. You cannot talk about all sizes in the spectrum. You will have to tell what is the mean, what is the standard deviation, and so on. Measurement is, of course, tricky because the coverage is very huge. Now, when we talk about this size, why the size is very important characteristics, I gave you answer, right? Because that will define where it will be going to deposit. That will also define which principle to be used for its measurement. If you are having large size particles, optical properties can be used to develop an instrument where your absorption, radiation, interaction can be used, right? OPC, optical particle counter, is an example. But now when the size of the particle is lesser than the wavelength of the light, then the things are completely different. You cannot use now optical particle counter if your size is lesser than 100 nanometer. You will have to rely on something else, right? That means that if you are not having that idea in mind, or you are not having that understanding what is the size you are going to measure, you cannot devise your own instrument. That information is crucial to be start before. And now, because I already mentioned that we have to express them in now diameter, that is a priori, or I'm assuming that the particles are spherical, which is not the case. Right? On spherical particles, examples will be very few. So what is to be done for the non-spherical particle is the next case. Right? How do we then get the diameter of a non-spherical particle, which will be ultimately linked to our theories and our development of instruments? And just one question. So you are knowing that when we are talking about the coronavirus, that was also one example of aerosol. So what was that instrument or technique which can measure the size of the coronavirus, right? So you keep on thinking during the lecture, right? So I have the follow-up lecture after the lunch, and then we are having interaction session during the entire workshop. So these questions are very simple, so you can think, and I am right now not providing the answers. So you will be getting the answers as we progress. Right? You also must be knowing that we are having an exam on the last day, right? And there will be some awards on the basis of that exam. So some questions will be linked to what instructors are delivering here as a part of their lecture. So you just keep on understanding, and you interact in such a way that you get that understanding, so that you ultimately get a feel of that exam as well. Now coming to the shape of aerosol particle, when the cases are like that, when the size is not, the particle is non-spherical in nature. So when we talk about now spherical particles, only liquid droplets are almost always spherical size because due to surface tension effects. However, mostly solids which are generated in atmosphere or you are generating in lab, they will be basically having the irregular shapes. And when the shape is irregular or it is non-spherical, then you require the concept of two. One is equivalent diameter and other is shape. These are slightly linked but slightly different concepts. When we talk about now equivalent diameter, so what you do basically, you mathematically assume there is some particle having some equivalence in terms of a property. Like a classic example is if you are defining volume diameter. Mathematically, you can always say if there is a non-spherical particle, it definitely will be having a volume. It could be a rectangular particle, any kind of particle. It is a chain-like aggregate, but mathematically it has some volume. You can measure that, you can estimate that mathematically as well. So for that irregular particle, there is a volume which is already pre-existing. When you are talking about now volume equivalent diameter, so it is the diameter of that sphere having the same volume as the particle. Right? So you are assuming that there is another particle which is spherical in nature mathematically, and the volume of that assumed particle is similar to the volume of the particle what you are having in question or what you wanted to model. Right? That is the thing. When we are matching the volume, the diameter will be called as volume equivalent diameter. But the matching could be done for other properties as well. Professor Tripathi mentioned that when we are talking about Modi impactor, when we are talking about PM 2.5 SEM plus and other things, there we refer to the diameter as aerodynamic diameter. So the concept is same again. When we refer to aerodynamic diameter, we are just matching some property which is important when the dynamics is happening in air. And when aerosol particles are in air, the most important characteristics for the particle is settling velocity. So your non-irregular particle will be having some settling velocity. If you are assuming that there is a mathematical or imaginary particle having the same settling velocity as your actual particle is having, right, then that diameter will be called as aerodynamic diameter. So aerodynamic diameter for a non-regular or non-spherical particle can be estimated in such a way. Right? You can find settling velocity for the actual particle. Then you assume there is a spherical particle having the same settling velocity. Diameter of that spherical particle is aerodynamic diameter. So you will be seeing that impactors, PM samplers, they will always be reporting their numbers in or results in aerodynamic diameter because they have drawn their characteristic curves using this theory. In the same way, when you now use scanning mobility particle sizer, they will be referring to mobility diameter because they are measuring electrical mobility. So mathematically, they are assuming that there is some spherical particle having the same electrical mobility as your particle is there. Similarly, this equivalence can be done for optical diameter as well. Optical particle counters are relying on that. Right? So this equivalence is very, very important when we are trying to use some instrument and when we are trying to measure some property for a non-spherical particle. You will see that our drag law and other laws will be assuming that particles are spherical. So if they are non-spherical, we will now find equivalent diameter and use the same. Apart from that, there is something which is called as a shape factor, which takes care when the particle is, because there are some shape effects as well, apart from this equivalence of diameter. When you are having some particle which is having a non-spherical shape, and you are comparing that with a spherical particle, when it is now traveling in air, you know that drag will be different when we are talking about a particle having some different shape compared to a sphere. So that equivalence or the comparison of the drag or the ratio of the drag is covered via shape factor. So different shape having the same volume may have the different shape factor, right? So a cube, a sphere, and something else as well, if we are having the same volume, right? They will be having the same volume diameter, but their shape factor will be different. If we are talking about now non-spherical particles, they have to be now characterized by equivalent diameter. That depends on which instrument or which property you are going to use. And apart from that, you should also be knowing the shape factor. You will be seeing that both these shape factor and equivalent diameter will be always coming in your estimations when you are using some theory, when you are defining some formulation for your particles. This is that representation. This is that irregular particle, and this is the sphere, which is having the same volume. So the diameter of this sphere is the volume equivalent, right? And now, if you can think, you must be knowing these things. You are clearly knowing these things when we are talking about now shape, right? So the shape is different for different particles. Dust you know, dust you have seen because that is scattering, right? So this is a common day-to-day example. And sea salt, soot, and other particles have different shapes. Doesn't matter. When we now understand the theory, shapes will be controlled by equivalent diameter as well as shape factor. Now coming to the next concept. So I am moving one by one. So size was the first one. When we discussed about size, that was the most important characteristics. Shape is the next one, which we just concluded. The third one is the concept of concentration. Because it is a suspension, and when we talk about suspension, air properties are integral part of your suspension. Aerosol is a two-phase system. And when we talk about now two-phase system, suspending medium is air. So the volume of air is always part of your calculations, right? That is the reason when we say concentration, we should not be bothering about the denominator part. It will always be present per meter cube, per centimeter cube, right? Per liter. That will be the volume of air in which the particles are suspended. You will only be worrying about what is the numerator for this concentration part, which is the property of the particles which are suspended. So when we talk about now concentration, mass concentration, when we say just microgram comes in numerator, right? So this is the mass which Professor Tripathi mentioned that we are using some PM sampler. We are collecting it on the filter paper. What is that mass which actually got collected on the filter paper will be expressed in microgram, milligram, gram, whatever you say, right? And when you divide it by the meter cube of the air for which this mass existed, right? You get the concentration, which is basically the mass concentration present in the air. We all very well know that this is the most important characteristic in terms of air quality index, right? PM 2.5 and PM 10 are the integral part of those 7 parameters which are measured for estimating AQI. And when we talk about now PMX, right? So this PMX is basically mass concentration only. So when we say PM 10, PM 2.5, so we are referring to mass concentration of particles having their aerodynamic diameter lesser than 10 micrometer or lesser than 2.5 micrometer. So you need not see now the units. PM10, PM2.5 will be having the unit either in microgram per meter cube, milligram per meter cube, depending on the level of the concentration. Mass concentration is easy to measure, right? And it has quite applications because it is directly linked to regulatory implications, right? We are making some policies based on what kind of PM levels are in air. Number concentration is the next thing for which you require some other instruments. Number per centimeter cube is the unit. Number per meter cube, you can also say, but it will become a very large number. You will see that number per centimeter cube. I have some numbers later on. We will just discuss those numbers as well. And then we will understand that why this range of instrument is important when we are talking about aerosol instrumentation basic. Number concentration has some other significance. First of all, when you are realistically, when the things are getting deposited, and I am relying on the mass concentration. Right? So if you can measure number concentration, that has to be measured because basically it is the input to code calculations. There are other characteristics or other concentration concepts as well, like activity concentration. You must not be knowing that, but if you just measure the radioactivity in air, that will also come in some unit. If you just measure that, it becomes in some becquerel. Becquerel per meter cube is that activity concentration, which is again some another concentration concept, right? For nuclear industry, this becomes very important. And now, because these concentration conditions are closely linked to operational, as well as regulatory requirements, we need to understand, we need to measure, and then we need to control if possible. You are knowing very well that WHO limits and AAQS limits, they give the units or they give this PM 2.5, PM 10, right, levels which we need to maintain, right? So microgram per meter cube is that standard which we are maintaining, right? So that we say that our air is clean or not, or we are following the level set by the government or not. Now, this again, another question that can you guess the mass of or the level of mass concentration right now in this air? Similarly, number concentration and possibly activity concentration as well. You can think about that. Maybe the last slide I am having where I will be depicting at least the mass and number concentration, which is as on today, right? We measured that mass and number concentration or the available data we have taken. So the information is live, right? So that information will be existing, but till then you can think that when I am talking about the mass concentration, PM 10, PM 2.5, what you are expecting in this room, what you are expecting in Pune. In the same way, when I am referring to number concentration, what you are expecting right now in Pune, monsoon season is going on. So what is that number per centimeter cube you are expecting at IITM when you are here to attend this workshop? We'll come back to this later on. There are other characteristics which has different implication for different context. One of them is density. Density of particles, right? So it is having the same unit as the unit of concentration. Density is also always that mass per unit volume, right? So when we say density, this is basically the mass per unit volume of particle. It has nothing to do with air, first of all. Concentration, the denominator was the concentration or the volume of air. However, when you refer to density, it is the mass per unit volume of particle itself having the same unit, but it is also the same phases, right? So that is the reason when you talk about liquid and crushed solid particles, they will have the same density. Water, whether you say that in the parent form or in the aerosol form, it will have the same density. However, now when you talk about some aerosol particles, we will cover that in some other lecture as well. We generally take some metal particles and we aerosolize that by something which is called as plasma torch aerosol generator. When we do this process, their density will be completely modified. It will not be the same density from which we started. So density of your aerosols can be completely different from your density of particles as well. Both are having the same unit. Generally, gram per meter cube we will use for density and microgram per meter cube or milligram per meter cube we will use for concentration. But concentration is a two-phase concept and density is a single-phase concept. Similarly, chemical composition, you know that there are some very high-end instruments which you will be seeing in Mahabaleshwar lab, where online chemical composition can be obtained. And why that is very, very important, because toxicity of aerosols ultimately, what after they are getting deposited in your lung, they have to harm or they have to give you benefit, depends on what is their chemical composition. If it is a drug, then it will be beneficial. If it is having some heavy metal concentration above some limit, then the lung will be exposed to that. So aerosol toxicity concept is built on the basis of, we will have to break. So it will be depending on what is its chemical composition. And because it is having direct implication to our health, that is the reason Professor Tripathi also showed you some slides where he was referring to the regional level chemical composition data. Because it is directly related to our lung deposition, lot of focus these days are on capturing the signature at regional scale. Apart from this, there are many, many characteristics, right? Charge will be covered in some other lecture. Tomorrow, growth factor and activation fraction will also be covered, which are basically characteristics which are important when the particles are interacting with water vapor. Similarly, optical characteristics, Dr. Padma will cover in the follow-up lecture, which will be important for understanding the effluometer and effluometer. So these things are the entire thing which will be building the core of aerosol characteristics, which should be known to you, right? So these are the characteristics which we should know, and these are the characteristics for which the instruments have been brought from different places, right? So ultimately, we want to measure all these characteristics. And as I mentioned, once we know these characteristics, we will understand aerosol better, and then we will be able to, first of all, visualize and control or mitigate whatever you want to say. That will be possible only after measuring their characteristics. We will have a break here, and after lunch, I will continue my lecture.
Thank you so much, sir. We will continue with this lecture after 2 o'clock. So now we will break for lunch. For the participants, the lunch is arranged at the IITM canteen.
डाउनलोड कर लिया था ये नहीं ये ड्राइव में So we are now continuing the lecture. I was talking about aerosol characteristics, right? So size, concentration, shape, chemical composition, charge, and there are many others. So you will be getting a chance to see the instrument which are specifically to measure all these characteristics. Now coming to the central concept of measuring size, because we know that when we are talking about now dispersity of particles, atmospheric aerosol spectrum is having a polydispersed distribution. There are all possible sizes, right from 1 nanometer up to at least 20 micrometer, 10 micrometer. Then even for your generation in laboratory and you are specifically doing some experiment, you are expecting sizes distribution which could be different for different context. We are having some hot wire nanoparticle generator in our demonstration session as well. You will be seeing that it will be generating particles of mean size 15-20 nanometer. Right, so that is that level of nanoparticle spectrum, and the dispersity will be very close to the 20 nanometer. So we are only expecting sizes from 5 nanometer up to maybe 100 nanometer for that particular case. While for nebulizers, atomizers, which again you will see in a one lecture and demonstration session, you will be seeing that we will be generating particles having mean size of 150, 200, 300 nanometer and higher than that. Now, when we talk about these generators, when we talk about atmospheric aerosol spectrum, now knowing the concept of central tendency of your distribution, and before that, what is that distribution itself, right? That should be known beforehand. So I am just referring to now that concept, and I am building that concept slowly, right? So that you understand the intricacies of this particular topic, which I believe is very, very important when you are talking about measurement of that size spectrum with using any instrument. So this is that picture which you are just comparing a typical urban aerosol number, surface and volume distributions. We will come to this number, surface and volume distribution later. And you can compare this graph with this graph, which is just comparing a typical urban condition with a rural condition. The plots are directly taken from some book. Right now, our interest is not to just go into the details of these plots. However, you can just see on the x-axis and you can see the top graph. So if you are just seeing on the x-axis, it is size. Size is on the x-axis for all the cases. And on the y-axis, you are seeing some symbols are there, but look at the units mainly. So the unit for this particular case is per centimeter cube. So we are basically referring to number per centimeter cube. Number as such has no unit. So we are referring to what is the total number or what is the number for a particular size. And so when we talk about this particular curve, our focus is on measuring number size distribution. Right? When you now move to the second curve for that same urban condition, you are seeing that the unit is now changed to micrometer square per centimeter cube. Now the same per centimeter cube had some particles, maybe 1,000, 10,000, 1 lakh, 100. Now all those particles, what is the total surface area is now plotted here. If you just integrate the area under the curve, or if you find the area under the curve, you will get the total micrometer square. However, if you are interested to see what is the total surface area between D1 and D2 particle size, then you can just take a slice of this graph. You can just assume that I just place a vertical line here, another vertical line here. So I will have a very small rectangle. The rectangle will be providing me the surface area for those particular sizes. Surface area of the particles which are having their sizes between that D1 and D2. That is reflected as micrometer square per centimeter cube. Similarly, if you are having interest to find micrometer cube per centimeter cube. So this is interesting. Now you see micrometer cube per centimeter cube, both are basically volume units, right? Micrometer cube per centimeter cube in terms of now dimension, if you think they are dimensionless. If you just see, but again, the concept we understood that when we are talking about concentration, micrometer cube is for the particles and centimeter cube is for your suspension medium, that is air. So you cannot just cancel like that. They are for the different phases. That is the reason we are separately writing that. And you are noticing that when we are having these things, so the shifting is also happening. So the mode for this distribution, which is the highest frequency, is coming here. However, for the surface area, it is coming here. In the volume, we are seeing two modes, right? So why this is happening exactly like this? That is first question, which I will try to answer in my follow-up slide. And second is then, when we are now comparing this with rural conditions, there are two differences which you can at least emphasize or you can notice. One is on the y-axis, you can just notice the numbers. Units are same. However, the upper limit was 10 to the power 2 into 10 to the power 5 here. And now it is just 5,000, roughly like that. Right? So that is expected when you are comparing a urban environment and urban environment to a rural environment, your numbers concentration is expected to be lesser. So it is in that sense perfect graph, right? So what basically we are right now talking about this, or why we are having interest to understand this, is because our range is enormous. We are referring to 1 nanometer, which is typical molecular cluster, to 100 micrometer, which is very close to small raindrops. Then 1 millimeter comes and raindrops will be coming, but they will no longer be aerosol particles. Their residence time in air is very small. We are just before that 50, 60 micrometer, where still they are meta-stable suspension. So there is a 5 order of change, right? From 1 nanometer, you are talking of 100 micrometer. So on the scale of now orders, you have moved 5 orders. So our coverage is 5 orders. So now our interest is to understand this distribution before measuring it. So now the next understanding will be how do we move here, what to do with these kind of distribution. So now if you see, when we mathematically talk about these kind of distributions or such kind of plots, the central concept is basically related to distribution function. So the ideal way would have been if even 1 nanometer aerosol particle is a combination of molecular clusters. So if you go to theory and if you just start with how many molecules are there in a 1 nanometer particle, that is one way to basically standardize that particle. You can always find how many molecules will be in 1 nanometer particle, 10 nanometer particle, 1 micrometer particle, 100 micrometer particle, but that is impractical way. There will be many molecules which will be now appearing in such calculations, right? So that is not a practical way, at least. Second way will be just to track each and every particle. You can see that how many numbers will be of 1 nanometer, then how many numbers will be of 1.1 nanometer. Depending on the accuracy of your instrument, resolution of your instrument, you can measure each size of particle and then report that, yes, for 5 nanometer particle, I am having the number per centimeter cube. For 10 nanometer, I am having this, but that is again impractical. So the only way is basically building in a histogram for your data. That is what is done. Ideal way is count and measure the characteristics of each particle. Because that is not possible, the practical way is you use bins. You talk about bins, D1 to D2, D2 to D3. And that is the reason now when you are now referring to some instrument, MODI, impactor, SMPS, you will be seeing that they will be having stages. And in those stages, you will be seeing there will be range of. So what we will do, what any instrument will do, it will just couple or it will just capture the particles in a particular bin. Right? And in that bin now it will measure the particles, and there will be similar kind of bins which will be ultimately integrated or added to get you the entire aerosol size spectrum. Now this is that spectrum. If you just start fundamentally like a histogram, right? So you just see. So if I'm just talking about this particular histogram, so it is roughly from 1.2 micrometer up to 2.5 micrometer. So we are having some number here, number concentration. So we are having some number for this histogram. Area of this histogram will be physically signifying you something. Similarly, there are many other histograms here, right? So if I now add the area of all histogram, I will get the total number concentration. If I just go to one particular histogram, I will get the number concentration for that histogram. That means that what is the lower threshold and what is the upper threshold for that histogram. Now the problem is there is one issue when you are starting the interpretation like this. First of all, our range on the x-axis is not uniform. When you talk about now coverage from 1 to 2 micrometer, 1 to 2 micrometer in terms of nanometer is the coverage of 1000 nanometer. 1 micrometer is 1000 nanometer, 2 micrometer is 2000 nanometer. So you have covered 2000 nanometer, right? So the number concentration when I am referring for this histogram is basically the number which I am expecting from 1000 nanometer to 2000 nanometer. So the range for me is 1000 nanometer. Difference is 1000 nanometer. Now, can I compare the same 1000 nanometer with this kind of histogram where the range will be very, very small? Maybe my first histogram is just from 1 to 50 nanometer. So the number which I am now comparing is only for 50 nanometer on the x-axis, and I am directly comparing with some number which is having the range of 1000 nanometer. So practically it is a completely wrong starting point for any histogram. If your size range is continuous or contiguous, what we say, when you are having 1 to 10, 10 to 20, 20 to 30, 30 to 40 nanometer, it would have been very easy. But that is not practical because your spectrum is of having 5 order of magnitude. You will have to club some sizes, and that sizes will be depending on what you are expecting in these sizes. So this issue of interpretation is coming because you have to have now a normalization of this height of the histogram with respect to the range. It will be nice if you can divide your number concentration by the range what you are having on that histogram. When you do such kind of thing, it is called as normalization. And if you do normalization, then your graph at least will be proper representation of your data. That is issue number 1 with this graph. Second, there is one more issue. The second issue is now, if you now just look at this histogram, what will be the area of the histogram in physical sense now? On the y-axis, we are having number concentration, having the units of per centimeter cube. On the x-axis, we are having size. So if I find the area and if I now see the unit for that area of that rectangle, right? So it will come as per centimeter cube into micrometer, which has no sense, right? So the area of this histogram, which I will integrate if I find the area of all the histograms, ultimately my unit will be per micrometer, or sorry, this, yes, micrometer into per centimeter. Right? Area of rectangle is just length into breadth. So I will be just getting the unit as per centimeter cube into micrometer. This is the second issue. I am not having a physical significance for my area of the rectangle or the area of the entire plot. And second is my histogram heights are not normalized with respect to the x-axis, which is the range. Right? So what should be done is the second step. What we should do to start with, we should normalize the height of each bin with respect to the width of bin. That can be done. Right? So you can just divide this number by this range, this number by the range on for that particular histogram, and you can just reshuffle your number and plot it again. Right? If you do that, now what will happen? The x-axis, now you just keep on tracking this units as well. The unit which was per centimeter cube for the first graph, right, now will become per micrometer per centimeter cube. Now you divided that number by your range as well. Right? So you have divided that per centimeter cube by your per micrometer as well. So your unit becomes now per micrometer per centimeter cube, right? If that is the case, right, now your area will become per micrometer into per centimeter cube into micrometer, right? Because the base is still on x-axis, it is still micrometer. On y-axis, now it became per micrometer into per centimeter cube. So micrometer will get cancelled and you will be left with per centimeter cube, which is now the number concentration, right? So if you do such thing, if you normalize both the issues are now sorted. First of all, normalization is now ensuring that your height is representative of your size range. Second, now the area of that particular histogram and the entire graph is now physically representing the number concentration, right? That will be your step number 1 when you are having your physical spectrum, right? So your size spectrum, when you are building, when you are having different side channels, you will have to get that data in such a way that you divide whatever you are measuring. If you are measuring mass concentration, you divide that mass concentration by the range. You normalize with respect to that, right? And second, then you will have to take care of the height of, and then both the issues will be sorted out. However, now, just to make, because now you are saying the entire thing is collapsing here itself, right? You will be now realizing in our demonstration classes that when we are now measuring number concentration, you will be seeing that a lot of number concentration will be for the sizes lesser than 300 nanometer, 500 nanometer, and only few numbers will be in the higher ranges. Right? So if you directly plot it just like that, you will get something like this. You are not seeing anything here. However, there are many channels there. But your scale of this choice of axis is wrong. So if you just take the log, right, then you will see it in a better way. Right? So now this is just the interval. I am not playing, I am not changing data. I am just changing the visualization for the same data. So I have just plotted, I have just now taken the x-axis in place of linear, I am taking the log axis now. If you do that, then you are getting the plot which looks like that, which is a very now nice plot compared to these two plots. It has no physical it has no issue in the physical significance kind of interpretation, and it is also now a proper plot, right? Physical significance is sorted out and we are able to see all histograms as well, right? Still now there are some issues. The issue is now if this is a textbook case which is taken from this book, and now if I go to data, I am not showing the table for this data, but you will see that the total number for this 0.1 to this is roughly same as here for this particular case. However, my interpretation is now indicating me that entire data is lesser than 0.1 micrometer, which is actually not the case, right? Right. So when I plotted it like this, so if you do this textbook, it is not possible to now do it here right now, but you can refer to this book and just see when they are discussing that in a very proper manner, right? Then you will realize that even this plot, which is not having an issue for physical interpretation, right? Which is also not having an issue in terms of your normalization, that is also taken care of. But still now when visually we are seeing that the impression which we are getting is not correct, right? So something else has to be done now. Right. So even we have taken care of the two fundamental issues. The third issue is now still persistent. It is existing. Now for that, now what we can do now, this is the same plot. Now if you see this, the plot you are seeing that per micrometer per centimeter. You just keep this I on in the y-axis, right? That will tell you what is happening. So when I say per micrometer per centimeter cube, this is basically that frequency distribution function. Right. So in that case, I have divided that by per micrometer, right? It just indicates that. If you just see, this is the same plot. Now the axis is changed to log. Nothing is changed. On this case, x-axis is linear. On this case, x-axis is log. Everything is right. You will be now doing data analysis. Same data you can take and you can just do the same calculation yourself, right? You must have done this previously as well. So if you just take x-axis is log, the appearance will look nice. Right. But as I said, the issues are still there because it indicates that this peak is having everything, while that is not the case. They are having equal contribution. Right. Now, for such kind of ambiguities, what should be done now? There is another way now, instead of now normalizing with respect to the difference of the diameter. If you can normalize with respect to the difference of the log of the diameter, right? You will now see, and you go back to your books, right? And you see on y-axis what they will do. Sometimes they will write as dn by dd. That means that the number concentration is divided by the range of the diameter. In some cases, then they will write dn by d log dp. So when we say now d log dp or d ln dp, that is basically they are now taking the log of those diameters and then they are subtracting that in the log space. So instead of now d2 minus d1, which is the difference of my size range, I am now referring to log d2 minus log d1. Right? That is basically now d log d. Right? Difference of log diameter itself. If you do that, if you do everything similarly, your data will be generated by instrument. It is same data for all plots. I am not changing data. But instead of now tracking D1, D2, D3, what I will do, first of all, I will find ln D1, ln D2, ln D3. Then I will find the difference of these logs. And whatever number I am having, I will divide that by this difference. Right? Then this plot will come. And now you have a look at this unit. When you talk about now log, right? Log of any quantity, log has to be now, you cannot take the log of a unit or a quantity which is having dimension, right? Log has to be taken for a number, right? So when I say now log D2 minus log D1, I will have to now basically, first of all, convert my diameter to a non-dimensional quantity. That is what is done basically. Every diameter you assume that it is divided by 1 micrometer. So D1 becomes D1 in micrometer becomes D1. When you divide it by 1 micrometer. Similarly, D2 in micrometer will become just D2. Now your ln D1 and ln D2 is basically a non-dimensional. It is just a number, right? And when it is a number, even if you divide, right, it is in denominator, it will have no unit. So when you are dividing your number concentration by that unitless quantity, right, your area will still be simply per centimeter cube. So our issue is also sorted out. And here we are seeing the same plot. This plot is same here, same data. But here now you are seeing the area under the curve under this first mode is similar to the second, right? So that visual bias is also gone, right? This is basically done when we are talking about plotting number distribution function. dn by d log dp is plotted on the y-axis. You will be seeing in SNPS, they will be having the option when you are having the data analysis classes, you ask them, right? Whoever is the instructor there, you tell them to plot the same data which you will be seeing on live on that screen. Y-axis, you tell them to take dn by dd, and y-axis, then you take them to take dn by d log dp. You will be seeing this difference, what I am trying to highlight. right? And then you will be seeing the same difference in terms of your surface area and in terms of your volume as well, right? So this is important concept. Now this unit issue is also gone. So when we refer to the dimension or this normalization with respect to the range, so we had the unit of 1 micrometer per centimeter cube. The unit is now per centimeter cube. Everything is now well set to move ahead, right? So this concept is, there is a difference in appearance when normalization is done with respect to the log of particle diameter. So you should not wonder now in your demonstration classes when you are seeing that on y-axis dn by d log dp will be coming again and again, right? That is just done for a proper visual appearance, right? Total area under the curve for all cases will be number concentration only, total number concentration, irrespective of your means entire size spectrum, right? So total number concentration will be now demonstrated by NT, and that will be, if you integrate this, every time it will be the same thing. Integration of that curve will be leading you to the total number concentration. But for our sake of understanding, for sake of visualization, we are just doing things like that. Okay, so just same thing now, if I just use a little bit of mathematics. So the aim is now to get the physical significance of distribution function. Now frequency distribution function is generally we refer to this, the term which is used for distribution function is frequency distribution function. It is also called as probability density function, right? So if you are knowing that, so this is already I explained. So our aim is basically to find the number of particles per centimeter cube having their diameter between d1 and d2. So dn is that aim, what we want, right? So what you are doing, you are multiplying something which is on the y-axis. That time it was per micrometer per centimeter cube with x-axis, which is just per micrometer, isn't it? Same thing I have written in now mathematics. So dd represents the x-axis and fd represents the y-axis, same histogram, right? So here this fd is basically what is termed as the frequency distribution function. You are operating your frequency distribution function on the size range, and then only you are getting the total number concentration or the number concentration for that particular histogram, right? FD is the central concept now when you are referring to size distribution. Now, have we seen FD so far? Yes, of course. So in the earlier graph, whenever I refer to per micrometer per centimeter cube, or even for that log case, on y-axis it was FD only, right? But that time I was not knowing that because mathematics was not introduced. But now I know that FD is something on the y-axis which will be multiplied with something on the x-axis, and then I will get the total number concentration or the number concentration representative of that histogram. FD is basically called as a frequency distribution function. It is exactly like an operator, right? Operator, there are many other operators as well. And now if you just integrate your FD from D minimum to D maximum, you are expecting the total number concentration, right? If you just integrate the area under the curve, you will get the total number, right? So this condition has to be maintained. Integration of D minimum to D maximum, FD has to be FD, right? So now if we see what is the unit for FD, this is already done now, right? Per micrometer per centimeter cube, if we are referring to our earlier graph, right? So that unit is per micrometer per centimeter cube. Now you will see that there is something else which is also called as cumulative distribution function, right? So when I say frequency distribution function, I am referring for sizes from D1 to D2. Cumulative distribution function just has a single difference. It will be now starting from your minimum to maximum. Ideally, minimum should be either 0 or minus infinity, but practically it will be D minimum, right? So when you say about now capital FD, you are doing the same thing which you have done here as well, right? You are integrating your FD. Don't bother about integration. Integration again means the area under the curve. So FD into DD is the area of one histogram. And when I say 0 to D, I am just adding area of all histograms from 0 to D, right? So this integration of 0 to D, FD, DD is what is called as a cumulative distribution function, right? And now you can easily think about the unit for FD. It is completely different, right? So it will not be having unit of per micrometer per centimeter cube, right? You can think, right? So this FD itself is now this my per micrometer is cancelled here. So FD will be having the unit for number concentration, right? You can think about that later on, right? So you can refer to book, and then this is the plot of your frequency distribution and your cumulative distribution. And why we need this, you will understand that in our impactor data. So suppose if I want to get the median for this distribution, this is a symmetrical distribution, things are easy, right? So you can easily say that wherever is the peak, that is your mode, something which is called as highest frequency. So there the mean and median will also lie. However, when you are having some distribution which is non-symmetric, then it will not be possible just by looking at the plot to get the summary statistic. For such cases, what should be done? We should plot this kind of plot. Why? Because the same plot is converted to this plot. However, when you are having this plot, you can simply go to 0.5 here, and corresponding to that, whatever is the diameter here, that will be your median. 50th percentile is what we say for that particular case, right? So cumulative distribution function has some distinct advantages when you are plotting it for your data, and you will be seeing the same for your impacted data. We will be using impacted data, but we will not be relying on the frequency distribution. We will in fact rely on the cumulative distribution. Using that cumulative distribution function, you can find the median and geometric standard deviation for your data. Now, the job is yours. Now you need to think about something else as well. So this FD without DD has no physical significance. FD without DD has no physical significance, but FD into DD has a physical significance. FD into DD is the total number concentration or the number concentration. But if I say what is FD, you can say that FD is frequency distribution function, but it has no physical significance, right? As such, you have to operate it on DD. There are many other mathematical operators like this, right? I will give you example like sine, right? Sine, when you say it is d by dx, right? So d by dx as such has no sense, but d by dx into fx has a sense, right? So similarly, you need to think about other operators which are having similar kind of, right, interpretation. Then mode, median, and mean can be now easily defined if you are having this FD, right? So when you have this frequency distribution function, you can use the mathematics, right? You can multiply your diameter with the frequency distribution function and integrate that. You will get the average diameter. So I have no time to touch on all details. But if you understand the concept till this point, it will not be very difficult to understand how the mean, median, and mode can be obtained in terms of distribution function. But this is important because you will be having the data, and for the data, you will not be doing integrations like tracking all the sizes. You plot the data, get the distribution function, and once you have the formula for your distribution function, things are done for you, right? Using that distribution function, you can find anything afterwards, right? That is the central concept. You need to understand, or you need to find the distribution function to start with. And for our aerosol, right, we know that the distribution function is log normal. There are many other distribution functions as well. Like this is a symmetric distribution function, which is called as a Gaussian distribution function, normal distribution function. It looks like a very nice symmetric distribution function. Central part is mean, right? You are having some dispersion. You know that 2 sigma, this just tells you that what is the coverage for this. So when I say now from here to here, I'm just talking about some coverage of the data, right? So this is x bar minus sigma to x bar plus sigma. So 67% of the data is covered for this case, right? So for a normal distribution, we have more or less very defined kind of interpretation. Now, when we talk about the log normal distribution, this is that plot, right? Which is now skewed plot. It is not exactly like this. So it is not very easy to predict where is the mean and median. Mode, of course, can be seen. Mode is the frequency, highest frequency. So this is visible. But where is that median and where is that mean, right? And they are not now symmetrical. They are not at the same point. This is a skew-symmetric skewness. So you will be seeing that the mean is here, median will be here, and mode is here. All parameters are at different places, right? But how do we get that? You get fx first. FD you get, then everything else will be mathematically obtained. This is now log normal distribution, and it is called as log normal distribution because it looks normal in the log scale, right? So log normal distribution, if you go into details, you will realize that it is basically, that is the reason it is called as log normal distribution, because it is a normal distribution on the log space. On the linear scale, it is having this shape, but on the log scale, it is having this shape, right? So aerosol size distributions are skewed, and they will be best described by log normal distribution function. So now when you are taking data for atmosphere using SMPS, right, you are expecting a distribution like this. And once you are seeing the distribution like this, your instructor should tell that how do we find that distribution function, and then how do we obtain mean, median, and mode for your data, right? Your software will also be doing that, but software may be just finding the mean mathematically, right? I am telling that your distribution has to be fitted by a distribution function, and once you get the distribution function, everything else even apart from this mean, median, mode, there are many other summary parameters that also can be obtained. So this X bar and sigma log normal distribution, they are here. So this is the question for you. Standard deviation is here. So in the case of log normal distribution, you know that it is called a geometric standard deviation. Slightly different concept comes, but you need to read it yourself, right? I need to cover other things as well. Now there is another concept which is very important for instrumentation persons, which is called as a moment of distribution function. Now this is basically, I have given an example as well. You see that you measure the number size distribution using instrument, but your estimation is for mass. You want mass size distribution, but your instrument is for number size distribution. What should be done? We don't have any other instrument just for a case, and we have some instrument which is either measuring mass size distribution or number size distribution, but you need the other picture as well, right? Then what should be done is basically covered in something which is called as a moment of distribution function. So in this case, what is done? So moment for a distribution function is you multiply your distribution function, frequency distribution function by your diameter to the power d. I will demonstrate it if you just take nu equals to 0. So d to the power 0 becomes 1. So it simply becomes fd into dd, which is basically the total area under the curve, which is total number concentration, right? So 0th movement is simply total number concentration, right? In the same way, if you just take nu equals to 1, then this becomes d to the power 1. So this becomes d into fd into dt, right? Now, if you think about the mean, right? So for estimating mean, we will be multiplying diameter by distribution function itself. So this is somewhere related to the mean diameter, right? So the first movement is related to mean. Basically, the first movement divided by the 0th movement is mean. For finding the mean, you will first find the total, right? And then divide by the total number concentration. Average diameter will be coming like that only. So that is the same thing which is done here, right? So similarly, now what you can do, you can find the other movements as well. Now we can think about physical significance of even second, third, fourth, and other movements as well. These are the questions to you. And now if you move forward, there is one central concept which is true for log normal distribution, which tells you that movement of a log normal distribution is another log normal distribution. This is central concept of aerosol instrumentation. That means that if you are having log normal distribution for number, right? Mass is nothing but it is basically diameter cube of number. If you just think about the mass of an aerosol particle, right? How you will get it? You will be just finding the volume and we will multiply by density. So volume of that aerosol particle will be d to the power 3, right? Same thing I was telling here only. So if you can just see d to the power nu, right? So mass is basically third movement of number, isn't it? So that means that if I am having the number size distribution, if that is log normal, then its mass size distribution will also be another log normal function, and there will be a connection now, right? That is the concept which helps us to have this relation, which is called as H-Coite relation equation, and which relates your count median diameter to mass median diameter. This also, I think we will touch during our instruction session in impactor, right? So how do we now get from CMD to MMD or MMD to CMD, right? That is one more. Now coming to some of the characteristic numbers. So I will be asking now many questions, which I am just keeping. I will share this PPT as well. So there are many questions which are now given to you, right? So you can discuss these questions whenever I am here. If you just need to think and then get the answer, possibly you will get the answers in your demonstration session as well. Right. After that, also you are welcome to ask anything later on as well. So when we are not talking about some characteristic number for important for aerosol technology, one is what is called as a Knudsen number. Now particles are in air, and air is also not steady. Air molecules are continuously moving. Right. Now when they are moving, there is something called as mean free path as well. Right. So they will be now hitting each other. Right. So there is an average distance which will be now for that mean free path, right? That roughly is 65 nanometer at NTP for air, right? So that means an air molecule is taking roughly 65 nanometer to travel to meet another air molecule, right? Now you assume a particle is of 1 micrometer and another particle is of just 1 nanometer size. Will they behave same? No, because one particle is even smaller than the mean free path, right? And the other particle is now having larger size, and for this air molecules are just like a continuous. This concept is basically coupled via Knudsen number. If you see, this is the same difference I am saying. For this particle, which is larger in size, air molecules are appearing as a continuous thing. That is the thing. This is called as continuum regime. However, now in the other regime, your air molecules are these, and particle is having closeness compared to the mean free path. So you cannot now treat your fluid as a continuum fluid, right? This regime is called as a free molecular regime. You will be seeing that your formulation will be different here and different here. Same coagulation, if you understand, it will be having different formula if you are interacting particles here. It will be having different formula if two particles are interacting in this domain. There are several other numbers like Reynolds number, Stokes number, Peclet number, and several many questions as well. One question I will answer here, and rest of questions you will need to think yourself. Now the question comes. We always see that the Stokes law is basically the basic law for your aerosol. Stokes drag law, right? When the particle is in air, right, it is stopped by the air molecule, and there is a drag force now which is acting on the particle. Now we always write that drag force will be only applicable when Reynolds number is less than 1. Right? We say that is the case because Reynolds number basically is the ratio of your inertial and this drag force, right? Viscous force. So the ratio has to be, now viscosity should, or viscous forces should dominate inertial forces. Then only the drag will come into picture. That is one way to look at that, right? But I can counter question that, then why that Reynolds number appeared here? Why that RE came into picture? Why not Peclet number came in this case? Why the Stokes number comes important, or that is coming only when we are talking about impaction, right? So there are many numbers in aerosol technology, and why they are appearing specifically for those cases, the answer is basically something which is a very mathematical, or something which is a central concept for all these things is, it is related to something called as non-dimensionalization of the governing equation, right? So this is another beautiful concept which you can learn if you are going deep into your books, and then only you will be able to understand these things clearly. I am just guiding you and just excite, or maybe these concepts are so exciting that you should be seeing that why Stokes number should be coming for impaction, why not for drag law, right? So these things will be coming if you understand the things like this. This is that drag law. I will not go into the details. You know that this is that particle. Its own weight is pulling it downward. Drag force is acting upward. So Newton's law is there. So there is a balance, right? So if you can find the difference, the buoyancy is also there. So this at equilibrium, these two forces will be equal, and ultimately when these two forces will become equal, the net force will be 0, right? So the acceleration will become 0, and then the particle will settle with that particular velocity. That is what is called as a settling velocity, right? So the details of mass you can see, but you see the settling velocity has some relationship where density is coming, diameter or radius is coming, and viscosity is also coming, right? But still that signal is not coming, that why that Reynolds number came into picture. For that, if we now go deeper, and if we see what is basically the Stokes drag law now, it originates from something which is called as a Navier-Stokes equation. The particle is moving in air, so it is a fluid flow characteristic case. In that case, what happens that when you are talking about Navier-Stokes equation, they describe the motion of fluid elements, and they arise from applying the principle of conservation of mass, momentum, and conservation of energy. If I am not able to go into the details, but you see this equation, this equation, there are many parameters which are shown here, density, acceleration, and forces which are acting here and there. Now, this is that equation which ultimately will be converted to Stokes law, right? And if that is the case, now what is done basically in that derivation, the parameters which are having dimension here, like this U, right? Like this T, like time, T has a dimension of time. Right? Now, if you non-dimensionalize that, you divide it by some characteristic time. Mathematically, you divide it by some tau. So this will become T by tau. Similarly, you divide U by some other U. U is velocity, so you divide by some other velocity, characteristic velocity, U by U naught. So if you just completely non-dimensionalize this equation, and another equation will be now written in a non-dimensional form, you will see that automatically that Reynolds number will be coming into picture. So when you are non-dimensionalizing this Navier-Stokes equation, which is the founding equation for drag law, right? You will see that Reynolds number has to appear automatically. And then you will realize that when that Reynolds number is appeared, this equation will lead to Stokes drag law only when this creeping flow conditions is coming, right? In detailing, you will have to see the books, but the concept is like that. Non-dimensionalization of this equation is very important. The next is Cunningham slick correction factor. Already I highlighted that your lambda and D, right? they have to have some impact on the drag as well. When your particle is smaller than the mean free path of the gas, then it is basically passing between the gas molecules. So the drag seen by the particles is even lesser, right? When it is larger, then in any case, the gas always will be obstructing it. In that case, the drag will be always appearing like that. So if you are not accounting for that, what happens is like this. So you see 1 micrometer, the CC is 1.164. So above 1 micrometer, even if you are not taking Cunningham slick correction factor, doesn't matter. But you see the result for 1 nanometer, 216 is the value for CC. And you see where is the CC appearing here. So your drag force, Stokes law, or the this estimation for FD is divided by CC now, right? So that means if you are not taking CC for 1 nanometer, your estimation is wrong by 200 times. In reality now, for 1 nanometer particle, the drag seen by the particle is lesser than, or it is 200 times less than the force which is provided by the drag law, right? And why it is happening? Because 1 nanometer particle is very, very small compared to the mean free path. It is slipping between the gas molecules, right? So it is having less drag, right? That central concept is coming into CC as well. So CC is that slip correction factor, and you will see that because everything else will be governed by FD, all parameters will be modified if you are taking CC into your account. Other numbers are also there, like Stokes number, which compares your relaxation time with stopping distance. So time is less, but this concept will be again coming for impactor theory. So the particles will be coming like this. So here discrepancies are taking turn, right? Now some of the particles which are having higher inertia will not be able to take turn with the air streamline. They will just impact on the plate. This is how basically PM samplers work. This is how basically any impactor will be working. However, when we now build the theory, then something will come like relaxation time, stopping distance, and the ratios of this relaxation time to the residence time or stopping distance to the characteristic length of the obstacle will give you Stokes number. So the graphs will be telling you that Stokes number should be greater than 1. It means that basically they are referring to this ratio only. So they are saying that your characteristic length of the obstacle should be more than stopping distance, or vice versa, right? So basically they are covering two important numbers, and then only the Stokes number is arising. Reynolds number will not come here because it has nothing to do with these two things now. Reynolds number came there because dimensionalization of the equation led to that Reynolds number. So these numbers are important in that sense. Okay. So I will just skip these processes. There is less time now, but this is that aerosol dynamic equation. Entire aerosol dynamic equation, if you see this particular term, you see nucleation happens when you are having a size generated from vapor, right? So this is the delta function. So it will only appear when nu equals to, so this will be 1 when nu equals to nu naught. Otherwise it will be 0. So that means this equation will be valid. This term will be only valid when nu is nu naught, v is v naught, you can say, right? So only for a critical size your nucleated particle will appear, right? Then those particles will grow. I have some plots, so we will understand that clearly. So this is the nucleation term. This is the term for coagulation. Right now we have no time. This is the term which is basically representing the size change due to condensation. And there are some other terms as well. So this entire equation is basically what is called as the aerosol dynamic equation, and which is then ultimately used for simulation of several properties. This is that overall picture which I just discussed. So from your condensable vapor, nucleation is happening, particle is appearing. Now this particle coagulates, it becomes a bigger particle. Condensation may happen on the particle, even the size will be bigger. Then these particles, this condensation may even go to CCN, and some chemical transformation may happen as well. Primarily the particle may be appearing like this as well. So entire processes are happening, and the aerosol dynamics is very complicated. All things are happening simultaneously. So when you are modulating, when you are modeling it, you will have to take care of everything at once. Modeling nucleation and condensation is different. Why? So nucleation because you are having a phase change. Condensation because you are again having a size change. And otherwise you are just talking about the physical characterization. Now just I am going to my last few slides. So complexity in aerosol measurements. Why aerosol measurements are so complicated? Gas. When we say I am measuring the properties of a gas, in that case I am having all, when I say now gas, like carbon dioxide gas, I just know that all molecules are of the same size, right? So that is the reason mostly concentration will be sufficient. I need not bother about the size spectrum. Every molecule will be having the same size. If I can just predict what is the temperature and what is the pressure, things are done. right? Then I will have entire things already ready with me. So concentration measurement will be sufficient. Thermodynamic properties will be determining several characteristics. There is no worry. And kinetic theory of a gas is a very standard platform which already exists. Nothing to worry. If you understand kinetic theory of gas, you can predict anything for your gas or air. Aerosol now, the size may vary by order of 5 decades. Complication number 1. No single instrument covers entire range. Complication number 2. Characterization will not be only involving size. It may involve concentration, chemical composition, and shape as well. And then even laws are size dependent. Coagulation of two particles which are nanometer in size is really completely governed by a different law when we are talking about the coagulation of 1 micrometer particle. And that is the reason, because free molecular dynamics is completely different from the continuum dynamics. I demonstrated not certain number is that concept which will be coming there, right? So that is another complexity. That is the reason this separate workshops are very, very important when we will be understanding these things. And that is the reason all instruments are coupled here. And now, ultimately, this is that history. So right now I am having no time, so I will share these things. This is the development of your several techniques, right, from 30s to these days. And this is that high resolution time of flight mass spectrometer, which you will be seeing in your Mahabaleshwar visit. And almost now many instruments, I think I have the one slide, which is showing that what instruments basically we are having here. And this slide is also telling you that when we are having measuring mass and size distribution, these instruments are available here with you now. You will be seeing all these instruments in your demonstration session, and which are almost covering entire properties, entire characterization as well. And I think coming to my final slide, these are the typical levels, but I gave you the question right at the start. If you just compare the mass concentration PM 2.5 in microgram per meter cube, New York, we just took these readings just when I started my lecture. So New York, the level was just 4. Beijing, which was 8. Delhi, it was 75. Mumbai and Pune were closed today. Diwali, you are expecting this PM 2.5 to rise. And if you are talking about dust storm, it is even higher. Now you look at this spectrum, we are trying to measure something which is a very small in number 4, 8, 10. And we are also interested to measure concentration in milligram or grams per meter cube. Right? So complexity is there. We cannot have the same technique. Everything cannot be measured by the same instrument. A very small concentration, high concentration, both has to be measured. Number concentration, similarly, if you talk about the clean room, class 10, 0.01 number per centimeter cube is the concentration. Indoor, the concentration lies like this. Outdoor, like this. Qualitative, the concentration is very high. And we measured concentration at IITM just behind this hall, outside this hall, morning, and the concentration was like that. Again, there is a range. So, the aim of this workshop is ultimately to explore the order of range. So understand. So how enormous is this range? Let us explore that and let us see the instrument which are basically covering this entire range. Right? Thank you very much.
Thank you, sir. Now let's move to the next lecture by Dr. Padma Kumari. Dr. Padma Kumari is the project director of the Lower Atmospheric Research using Unmanned Aerial System Facility, LORAS, at IITM. This project aims to capture crucial yet undersampled meteorological and atmospheric observations in the lower atmosphere, significantly contributing to our understanding of climate and atmospheric processes. Her area of research is aerosol cloud radiation interactions. I invite Dr. Padma Kumari to the stage to deliver her lecture. Welcome.
Good afternoon, all. Thank you, Dr. Manish, for covering almost all the aspects of aerosols. And here I will quickly, as we are running out of time, I'll quickly touch upon the scattering, absorption, and aerosol radiation properties. So in the last two lectures, we had a very good introduction about aerosols, their sources, and how they are produced, and so on. So basically, we classify aerosols as natural aerosols and anthropogenic aerosols, which we are all aware of. Like natural aerosols coming from variety of sources like sea salt, mineral dust, volcanic eruptions, CMS, and so on, and anthropogenic aerosols, which directly or indirectly, we are also responsible for this. And then, but still, why are we concerned about these aerosols? Because we are concerned because they play a very significant role in very two important aspects in our life. That is, one is climate and the other one is health. So, under aerosol physical characterization, most of these aspects are already covered by my previous speaker. So I will not go much detail into this. But when coming to this aerosol optical properties and so on, we need to know aerosol size distribution. This is very important, and it is characterized by number, volume, and mass, has already explained my previous speaker. And what we should remember is different modes, like nucleation mode. This is the range, and they are freshly formed particles from gas to particle conversion, and Atkin mode from 0.1 to 0.1 to 0.1 micron, and these particles have come from combustion and secondary sources. Generally short-lived they are, and accumulation mode found by coagulation of smaller particles or gas-phase condensation, and they have longer lifetimes and are important for cloud condensation nuclei. So, and then comes to last coarse mode, all particles above 1 micrometer, and this includes mechanically generated particles like dust, sea salt, pollen, and spores. And now this is a typical textbook figure which explains different modes of aerosols, which is very important to understand. And here, this talks about the physical processes involved in the size distribution. And these are the modes. And to measure these modes, we need very sophisticated instrumentation. And one single instrument cannot give us all the modes. So we should have, depending upon the area of research, we should use different instruments to capture the entire size distribution of aerosols present in the atmosphere. And now directly coming to the aerosol radiation interactions. And here, as we know, sun is the ultimate source of energy, and sun provides the energy that drives the Earth's climate, but not all of the energy reaches the top of the atmosphere, does not come to the surface. So in between, what is happening like? Sorry. Hello. So this schematic shows the various sources of aerosols, like I mentioned, natural sources and anthropogenic sources, and some are directly injected into the atmosphere, and some are formed in the atmosphere by gas to particle conversions. And these aerosols, they enter into the atmosphere and form layers at different altitudes, depending upon their life and then their characteristics. So, and they get interacted with the incoming solar radiation, and thereby they scatter most of the radiation back, and they absorb, and a part of it, a fraction of it is being transmitted to the surface. So here we have direct radiative forcing, and then aerosols also affect indirectly through clouds. And in this process, we have aerosol size evolution from nucleation, coagulation, condensation, which very nicely Dr. Manish has explained to us. And the size of an aerosol determines how effectively it scatters or absorbs light. That is why size distribution plays a very important role. And during the interaction of light with aerosols, which depends upon wavelength and optical characteristics of aerosols, there are two main phenomena like scattering of light and absorption of light. So here, scattering aerosols are particles in the atmosphere that predominantly interact with the light and by redirecting back or scattering the incoming radiation without significantly absorbing it. Example of scattering aerosols are sulfate, nitrate, and sea salt. And the amount of scattered light depends not only on the wavelength of incident and the scattering angle, wavelength of the incident light and the scattering angle, but also on the physical parameters such as shape, size, and refractive index, which is already covered. And these aerosols, why these scattering aerosols are very important, because they play a crucial role in cooling the Earth's surface and altering the radiative balance by reflecting sunlight back to the space, which directly impacts the Earth's climate and, of course, the atmospheric visibility. And now the absorbing aerosols, they refer to the aerosols that absorb light. And the sources of absorbing aerosols include biomass burning and other combustion processes and dust entrainment. And aerosol light absorption in the shortwave spectral region is dominated mostly by the black carbon, with additional contributions coming from your brown carbon and as well as from the mineral dust. And these aerosols play an important role in the Earth's atmosphere in terms of direct and the semi-direct forcing and also visibility. Now, what is happening is the electromagnetic energy is transformed into thermal energy, and which heats up the absorbing particles as well as their surroundings, and thereby reducing the incident solar radiation that is reaching the surface. And then the heating of the absorbing aerosols changes the local atmospheric temperatures, which thereby influences your relative humidity, atmospheric circulation, and stability, and thereby cloud formation and lifetime. And one very good example of this absorbing aerosols are deposition of absorbing aerosols on snow and ice that reduces the surface albedo, leading to melting. And now this is a very typical example which clearly explains about the direct effect and semi-direct effect of aerosols. And here, aerosol, more the aerosols we have with low aerosol loading, we have less scattering, whereas more aerosol loading, we have increased scattering, and thereby reducing the radiation reaching the surface. And now atmosphere has a mixture of both scattering and absorbing type of aerosols. So in case of absorbing aerosols, they absorb the light and then they heat up the atmosphere. And then the clouds that are formed at those altitudes, they get evaporated because of this heating. And thereby it is also called as cloud burning effect. So this is the direct effect, and the other one is the semi-direct effect. So now the aerosol scattering and absorption processes that determine the light, that determine the intensity, light intensity that is in the surface. So there are, and these aerosols that are suspended in the atmosphere, how important they are in terms of radiative balance of the atmosphere. So the aerosols directly interacting with the radiation is called direct effect. And also you can see here the size also matters here. The smaller the size, we have less scattering, and the bigger the size, we have more scattered light. And then if you have absorbing aerosol coated with the by another scattering aerosol, then it is something different. So how do we measure these? The light coming, the scattering of light, that is very important in any plays an important part in any instrumentation. So how do we measure this? And by measuring the scattered light, how do we come to know about the size of the particle? And also another important thing is whether it is scattering or absorbing. So that is also very crucial to understand. And then the aerosol forcing mechanisms are classified as direct effect, light scattering and absorption, surface, which leads to surface cooling and atmospheric warming. And we have And first indirect effect and second indirect effect where clouds come into play. And you will study about this aerosol cloud interactions in tomorrow's lecture. And now semi-direct effect, which leads to cloud warming to do atmospheric heating. And now understanding the properties of aerosols is very important because they have the ability to affect not only visibility, global and regional climate change, but also our health. So to understand the effects of aerosols on climate and health, measurements of their optical and physical properties are very much essential. And then this particle number size distribution, which we have already covered, and concentration, and then aerosol light absorption and scattering in the atmosphere. So these are the properties which we should know to understand the role of aerosols in the climate and our health. And many aerosol assessment techniques in the atmosphere are based on this scattered light by aerosol particles. Now coming to optical particle counters. So these optical particle counters, they use laser diode to measure the number concentration of aerosol particles in different size bins or channels within. And particles are sampled into the instrument and travels perpendicular to the laser beam. And then the basic principle in optical counters is that it measures the amount of light scattered by individual particles as they pass through a focused beam of light. And a fraction of the scattered light is collected and directed to a photodetector, where it is converted to a voltage pulse. So the scattered light is then used to classify the particles into different channels used and based on the proportion of light scattered forward. And then this is the instrument which will be demonstrated after this. Here, the instrument's working principle is based on 90-degree light scattering, and it also has a filter sampling. So this will be demonstrated in the next session. And then measurements of aerosol absorption. Here, the basic principle is filter-based instruments are used here, and which measure, here accelerometer is a soot monitor which measures the attenuation of light through a filter and on which the aerosols are deposited. And light of different wavelengths are used to quantify absorption and differentiate between different aerosol types like black carbon, brown carbon, and so on. And the difference in attenuation between exposed and blank filters is proportional to the amount of light absorbing aerosol, carbonaceous aerosols that are captured. And here the attenuation coefficient is converted into absorption coefficient using the correction factors that account for scattering effects and filter loading effects. And then accelerometer, this is, you will also see this in a while. So, and it has the basic components such as light source, filter tape, air pump, photodetector, optical system, and a control system. So I'll not go much into this. So this is the basic picture which explains you the light source, and you have a filter samples here, and we have one reference also, a blank filter. So the light detected, these are the photodetectors. The transmitted light is detected by these photodetectors, and then attenuation is computed. So the difference between different filters, black carbon concentration is estimated based on this differences in the absorption on different filters. So this also will be see, you'll have a filter tape here. And once the when the maximum attenuation is reached, then the filter it goes to the next level, and it is continuously, it will be operated. And so it is a continuous monitoring as compared to what in the previous lectures we have seen. We have to manually operate to collect the samples. However, in this case, it is no manual intervention is required. And next, coming to accelerometer, this is an instrument used to measure the scattering coefficient of aerosol particles and providing information about the amount of light scattered by aerosols in the atmosphere. And this scattered light, this is also very important parameter, which is essential in terms of Earth's radiation budget calculations. And it operates based on the measurement of light scattering by particles suspended in the air. And here the light source typically an LED or a laser beam, emits a beam of light into a chamber containing the air sample. And as the light interacts with the suspended particles, some of it is scattered in different directions. And the scattered light is captured by photodetectors placed at specific angles. So this instrument will also be demonstrated in a while. And the intensity of scattered light here is proportional to the number of particles and their properties, such as size and refractive index. And the nephelometer measures the light intensity and converts into the particle concentration using a predetermined calibration factors. And the next parameter is aerosol optical depth. I think you all are aware of this. And it is a measure of the extinction caused by scattering and absorption by aerosols along the vertical column of the atmosphere. And this is a simple Lambert-Beer's law, and where I is the intensity of the light, and B is the extinction coefficient, and K is the distance in meters. And retrieval of AOD, we use ground-based measurements, handheld sun photometers. I guess most of you are aware of this instrument. And it measures AOD in 5 different wavelengths. And also we also use sun photometers or sun sky radiometers. And this is a sun photometer which we are having at IITM, which will also be demonstrated. And this is a multi-channel automatic sun and sky scanning radiometer that measures the direct solar irradiance and sky radiance at the Earth's surface. And it makes measurements at predetermined discrete wavelengths in the visible and near infrared parts of the spectrum. These are the different wavelengths used here. And this sun photometer is a part of the Aeronet. I think all of you are aware of this, which is Aerosol Robotic Network program. It is initiated by NASA, and this provides globally distributed observations of spectral aerosol optical depth, inversion products, and reciprocal water vapor. And one can look into this site to get the different parameters, and all around the world. These sun photometers are you will be able to access through this link, and various optical depths. You can even download the data and process for your location, interested location. Yeah, thank you. And now for further discussions and all, we'll be meeting in that gallery. All the instruments which I have shown will be demonstrated, and any questions and all we can discuss there. Okay. So that we can have more time for demonstration and hands-on.
Thank you, ma'am. So there are few announcements. Now we'll proceed to the instrument demonstration followed by data analysis. So already this has mailed you about the groups. So we'll show the group here also, you can see. And group 1 will go for accelerometer disk. Group 2 optical particle counter disk. Group 3 MODIS as cascade impactor disk, and group 4 will be here only. So group 1 can proceed for accelerometer disk. There will be tea break 4 to 4:30, and that's a reception only. So group 1 is to the accelerometer desk. It is at reception. We have already mailed you this list, so you can get it from your mail also.
जूम करके लेना सकते हैं, एक ही पेज जूम करके एक इधर जूम करके लेना दिख नहीं रहा, ट्राई करो।